The red-green refactor workflow is a core component of the test-driven development, or TDD methodology. Now, this approach really emphasizes the importance of testing and iterative development. So let's break it down. The essence of TDD is to start with a test that defines a desired outcome, like what are we aiming for? Then you implement the smallest chunk of code necessary to pass that test. After that, it's all about refining your code for better maintainability and clarity. Today, we're diving into this workflow, splitting it into 3 distinct phases: red, green, and refactor. We'll explore each of these with some Python code examples as we develop a web application using Svelte and Playwright. So grab your coding gear and let's get started on this amazing journey of coding awesomeness together. Now let's dive into how we can set up a basic testing structure for our birthday component using Vitest and the Svelte testing library. First up, we'll import some key functions you'll need. We're talking about describe, it, and expect from Vitest, plus render and screen from the Svelte testing library. Great! Now we'll set the stage for our test suite by calling describe, which helps us group our related tests for that birthday component. Inside this suite, we're going to define our first test case with the it function. So this test has a specific goal. We want to check that when we render the birthday component with the name Hercules as a prop, it should pop up and be visible in the document object model, or DOM for short. We're using the render function to create an instance of that birthday component, right? So we'll inject our name property there. Now, after we render it, we'll throw in an expect statement together with screen.queryByText to ensure the text Hercules is indeed present and displayed in our rendered output. Aha! This step is super important because, heads up, the test is expected to fail at first. That's actually a good thing. It confirms that the component's functionality isn't there yet, which is just perfect. It's a solid starting point for our test-driven development, or TDD process. Now, let's implement the birthday component that we defined in our test. This component is designed to accept the name prop and display it dynamically within the HTML. So we kick things off by using a script tag where we declare export_let_name. This line indicates that the name variable is a prop that can be passed into the component from its parent, allowing for some serious flexibility and reuse. Next, we focus on the template part of the component. Within the span tags, we use Svelte's curly braces syntax, name, to inject the value of the name prop directly into the DOM. This means whatever value gets supplied when the component is rendered, like Hercules in our test, will be displayed as bold text on the web page. By keeping the component simple and straightforward, we've taken a crucial step toward passing our failing test, confirming that our implementation is effectively displaying the data provided. After creating this component, we can rerun the test suite to make sure it passes, marking a significant milestone in our TDD cycle. Next, we're going to enhance our birthday component to support not just a name, but also a date of birth. This means we'll be adding a new prop for the date of birth, which will really enrich our component's functionality while keeping its structure open for future enhancements. So let's dive into the new implementation. We start by exporting 2 props, name and DOB, allowing us to pass in a person's name and their date of birth when we use this component in our application. In the template, we're structuring the rendered output with a div that will contain 2 span elements. The first span will display the name in bold, using a strong tag to make it stand out visually. The second span will simply show the date of birth. This updated component not only adheres to the principles of clean design, very important, but it also preps our application for any future features we might want to throw in, like additional styling or enhanced data handling. Now, with this setup, it's crucial to revisit your unit tests to ensure they cover the new date of birth prop. This step is key to maintaining our coverage and functionality as we move forward in the development process. So there you have it, a solid foundation for our birthday component. Next, we're going to dive into writing some unit tests for our birthday component to make sure it functions as it should. The very first test checks whether our component correctly displays the name of the person. To do this, we'll use the render function from our testing library to create an instance of the birthday component, passing Hercules as the name prop. Now, after rendering, we need to ensure the name is visible in the DOM. We're going to assert that when the prop is set right, we should definitely see Hercules up on the screen. Cool, right? Now let's jump into another test. This one will confirm that our component also shows the date of birth correctly. Just like before, we'll render the birthday component again, this time including both the name and the date of birth props. Then we'll assert that the date of birth, 1994-02, is indeed visible in our rendered output. With this, we can verify that our component handles multiple props effectively. Altogether, these tests really solidify that our birthday component works as intended by confirming the presence of essential information, which is key to reliable software. By expanding our test coverage in this way, we build confidence in how our component functions as we move through the red-green refactor cycle. So, let's consider how we can really expand this workflow beyond just those individual components. The beauty of test-driven development, or TDD, coupled with the red-green refactor workflow is that it scales beautifully, whether you're going solo or working with a team. It helps align discussions and decision-making all around those shared coding goals. For example, if a team is tasked with building something a bit more complex, like, say, user account management or integrating an API, you can just apply those same principles. The initial steps here, they'd involve spelling out tests for the expected behaviors, implementing just enough code to make those tests pass, and then refining that code. This could get pretty intricate and might even bring in additional testing frameworks, like Playwright for end-to-end testing. And guess what? Pairing Playwright with Vitest ensures that both your unit tests and integration tests stay rock solid as you evolve your application's functionality. How awesome is that? All right, let's wrap this up. The red-green refactor workflow is an absolute game changer for developers. By cycling through test creation and refinement, you're not just writing code, you're systematically honing a high-quality code base. TDD isn't just some method, it's a whole mindset that gives you the confidence to really believe in your code. You'll find you can adapt your application and tackle those daunting challenges with less fear of bugs creeping in, all while ensuring each piece functions perfectly. With a little practice, this workflow becomes second nature, arming you with the skills to take on even more complex problems in your development arsenal. Just think about it. Having that meticulous attention to testing and refining results in a product that not only performs well, but is also clean, super maintainable, and ready for enhancements down the road. Embrace this approach, and you'll discover that as your software evolves, so does your expertise as a developer. And trust me, there's a real satisfaction that comes from the work you produce. In this video, we're going to dive into building some awesome Svelte components while applying test-driven development principles. We're kicking things off by creating a component specifically designed to display a list of birthdays. We'll follow a systematic approach that touches on tests, implementation, and refinement, basically ensuring our code is clean and effective. So far, we've learned about the red-green refactor workflow, which is super fundamental to test-driven development, or TDD for those in the know. Remember, it's all about structured, iterative software development through testing. We've explored those 3 critical phases, starting with a failing test, which is the red phase, then moving on to implementing just enough code to pass that test. Yep, that's the green phase. And finally, we refactor our code for better quality and maintainability. We've been discussing how all of this applies to our birthday component built in Svelte, along with the tests that evolve through each of these phases. This process not only boosts our code quality, but also nurtures a mindset that grows confidence and adaptability in software development. Now, let's create a dynamic Svelte component that lists those birthdays while displaying relevant info. All right, here we go. Let's set the stage. Imagine we're building an application to manage a birthday list, whether it's for friends, family, or your favorite celebrities. Today, we're focusing on creating a birthday list component that allows us to add, display, and even remove birthdays. We'll be harnessing the power of Svelte, which is honestly a fantastic framework that makes web application building so much fun. So let's get started by setting up our first test. Now, let's implement the initial test for our birthday list component using the Vitest testing library. We begin by importing the necessary functions and libraries, describe, it, and expect from Vitest, along with render and screen from the Svelte testing library. Inside the describe block, we create a test suite specifically for our birthday list component. Next, we set up our very first test case using the it function, declaring that the component should display a list of birthdays. Here, we define an array of birthday objects that include names and birth dates. This data will serve as props for our birthday list component. All right, moving on. We render the component and pass that birthdays array as props. After we've rendered it, we establish assertions to verify the visibility of names like Alice and Bob on the screen. These assertions make sure that when the component is working correctly, we'll see those names rendered just as we expect. But hold on, whoa! Since we haven't actually created the birthday list component yet, this test will initially fail, kind of like a gentle reminder of the essence of test-driven development. We start with a failing test to guide our implementation. Now, let's take a closer look at implementing the birthday list component. We're kicking things off with a script block where we're exporting a variable named birthdays, and we're starting it out as an empty array. This export lets us pass in an array of birthday objects whenever our component is rendered. Inside the template, we're using Svelte's heach directive to create a loop over the birthdays array. For each birthday object, we generate a list item, or LI, to display the person's name alongside their date of birth. It's a seamless iteration that showcases Svelte's reactivity. Whenever the birthdays array changes, the DOM updates automatically. By structuring our code in this way, we establish a clear and reusable component structure. It's so straightforward, right? This simplicity is powerful because it allows for easy updates and maintenance. With this solid foundation, we can effectively manage and display a list of birthdays. It's all about helping users celebrate their loved ones' special days, and isn't that what it's all about? And as we finalize this component, we're gearing up to integrate some exciting new features, like removing birthdays, ensuring our application evolves to truly meet user needs. Now, let's dive into how we can implement the functionality to remove a birthday from our list. First things first, we begin by exporting the birthdays prop, which allows us to receive an array of birthday objects. Now, let's introduce a new variable called current birthdays. We'll initialize it with a copy of the incoming birthdays prop. This creates a local state that we can manipulate independently of the original prop. So, to make removal happen, we need to define the remove birthday function. This function takes a name as a parameter and updates current birthdays by filtering out the birthday that matches the name. Awesome, right? When a user clicks the Remove button beside a birthday, bam, this function is triggered, effectively altering the state and kicking off Svelte's reactivity. Now, over in the markup section, we're using the #each block to loop through current birthdays and render each birthday as a list item. For every list item, we display the birthday's name and date of birth along with a button that calls Remove Birthday when clicked. This interactive feature perfectly demonstrates Svelte's seamless handling of state and those automatic DOM updates, making sure the user experience stays dynamically in sync with any changes in the data. So cool, right? All right, let's dive in. Now, let's implement the additional test to ensure that our remove feature functions correctly. In this section, we start by writing a new test case within the describe block for the birthday list component, where we structure it to validate that a birthday can be successfully removed from the list. We first define an array of birthday objects, including Alice and Bob, to simulate the initial state of our component. After rendering the birthday list with the provided birthdays, we utilize the screen.getByText method to locate the remove button associated with the birthday we want to delete. Picture this, a user clicks that button. So we use fireEvent.click to simulate that action. Following the interaction, we check whether Alice is still present in the document using screen.queryByText. If it returns null, yay! It confirms that our functionality to remove a birthday works as expected. This really reflects the core principle of test-driven development. By verifying the outcome of our changes through tests, we reinforce our confidence in the component's behavior. This cyclical process of testing and refining helps solidify both the functionality and maintainability of our code. Now let's dive into enhancing our birthday list component with some styling, shall we? By defining specific styles right within a style tag in our Svelte component, we can really leverage scoped styling to give our list a fresh and accessible look. We kick things off by customizing the unordered list, or UL. We're stripping away that default list style and padding for a cleaner layout. Each list item, or LI, gets a soft background color along with a subtle border and those lovely rounded corners to really make it pop. Oh, and let's not forget about the extra margin and padding we've added. This spacing helps separate each birthday entry, making it so much easier to read. Moving on, we're focusing on the buttons users will click to remove birthdays. By applying a vibrant background color and white text with rounded edges, we create a super inviting button that just screams, "Click me!" Plus, that hover effect, it darkens the button's background, giving instant feedback. Whoa, it's like saying, "Yep, I'm ready for action." So, in summary, these styling enhancements not only make our component visually appealing, but they also greatly improve the overall user experience. It all helps promote clear interactions and, honestly, a more enjoyable usage experience. As we wrap up our exploration of the birthday list component, let's take a moment to reflect on what we've accomplished today. We embarked on the entire test-driven development journey, starting from defining our tests, then moving on to implementing our component, enhancing its functionality, and finally fine-tuning our code. Each step was like a building block, reinforcing our understanding of both Svelte and TDD. We've seen firsthand the importance of kicking things off with a failing test, that thrill of seeing it pass, and how crucial refactoring is for maintaining quality. Throughout this entire adventure, you've also experienced how Svelte makes creating reactive web applications feel like a breeze. The way it seamlessly integrates reactive data binding, event handling, and layout structure really highlights the power of this framework. Not only does it support rapid development, but it also keeps our code clean and maintainable. So, in summary, we've laid down a solid foundation for creating Svelte components using a TDD approach. From building our simple birthday list to weaving in more advanced functionality, our journey underscored the necessity of iterative development processes. Remember, every small iteration is a stepping stone toward crafting robust, user-friendly applications. Thank you for joining me in this session. Keep applying these principles, and you'll notice your development skills blossoming exponentially, empowering you to tackle even more complex applications with confidence. Until next time, happy coding! The red-green refactor workflow is a cornerstone of test-driven development, acting as a structured process for software development. By following this cyclic practice, developers can approach programming with clarity, precision, and confidence. So today, let's unravel this workflow and translate its theory into actionable coding practices in Svelte with Python. So far, we've learned about building Svelte components using test-driven development, TDD for short, by creating a birthday list component that displays and manages a list of birthdays. We've explored the red-green refactor workflow and applied it to write tests, develop functionality, and refine our code. This process really emphasizes the importance of maintaining code quality and adaptability while enhancing the user experience through effective styling. Our journey has shown the power of Svelte in crafting reactive web applications, which gives us a solid foundation for future development. Now, folks, let's dive even deeper into the depths of the red-green refactor workflow. Now, let's dive into how we can implement our first test using the Vitest framework, which sets the foundation for the red phase of the red-green refactor cycle. First off, we'll start by importing essential modules from Vitest, specifically describe, it, and expect, along with the handy render and screen utilities from the Svelte testing library. So let's define a test suite for our birthday component using the describe function. Within this suite, we'll encapsulate our individual test using it, clearly stating that our aim here is to verify if the component displays the provided name correctly. To simulate user interaction, yep, you guessed it, we employ the render function to mount the birthday component while passing the name prop. And in this case, let's use Hercules. After rendering, we'll query the DOM using screen.queryByText to check for the visibility of the name Hercules. This assertion is crucial because if the name isn't found, our test is going to fail, which embodies the essence of the red phase, establishing a failing test to guide our future development. By meticulously defining our expectations right from the get-go, we ensure a solid starting point for our development efforts. Let's implement the following code to ensure that our birthday component correctly outputs the name passed to it. We start with a script tag where we declare a prop called name, which allows the component to receive data from its parent. This is achieved with the export let name statement, indicating that name is a variable that can be exported and used as an input for the component. Next up, we see how this dynamic data is presented within the component's markup. In the HTML, we utilize a span element that wraps the name variable inside a strong tag. This semantically emphasizes the name by making it bold. Now, those curly braces, name, they are Svelte's way of inserting JavaScript expressions, allowing us to directly display the value of the name prop in the rendered output. By putting this code in place, we can ensure that when we assign a specific value to the name prop, like Hercules, it will dynamically reflect in the user interface. This makes our component reactive, adapting seamlessly to the data fed into it and showcasing the principles of test-driven development. Isn't that cool? Now let's implement the following code to enhance our birthday component by adding a new property for date of birth. Within the script tag, we'll declare two exported variables, name and DOB. This little move allows us to accept both properties from the parent component, which means we can dynamically render a person's name along with their date of birth. Next up, we need to display these properties in our component. We're going to use two span elements to do just that. The first span wraps the name and will emphasize it with some strong formatting. This helps it stand out visually, which is super important. The second span? That one's going to show the DOB in a clear, unobtrusive way. By structuring our component this way, we're sticking to the principles of component-based design in Svelte, ensuring our birthday component stays flexible and maintainable. This change not only enriches the information we present, but it also sets us up nicely for any future enhancements we might want to make, like adding even more features down the road. Remember, every time we add something new, it's a great idea to revisit our tests to ensure they're still validating the functionality of our updated code accurately. So, let's take a look at how we can expand our test suite to include the functionality for displaying a date of birth within our birthday component. So, we're going to kick things off by defining a new test that checks if the date of birth is rendered correctly when we pass it as a prop. In this code, we're using the popular testing library in Svelte, right? First, we render the birthday component with both the name and the date of birth props. It's super important to use the render function to mount the component properly so we can perform our assertions on its output. Next, we utilize the expect function along with screen.queryByText to check if the date of birth is visible in the rendered output. This assertion helps ensure that when we pass the date 1994-02-02, it shows up correctly in the user interface. If the test passes, it's like a big thumbs up. We can confidently say that our implementation meets the specified requirements. Through this process, we're really keeping the cycle of writing tests that guide our development, reinforcing our commitment to quality and functionality as we navigate through the red-green refactor workflow. The beauty of the red-green refactor workflow is its iterative nature. By repeating this process, write a failing test, make it pass, and then refactor, you build your software incrementally and, with strong guarantees about its correctness. Plus, this method really opens up the lines of communication among team members as you develop software, fostering better understanding and collaboration. Now let's take a moment to reflect on some broader implications of implementing the red-green refactor cycle in your projects. It declutters your workflow by creating a strict framework to follow, which can seriously reduce development time and improve code quality. And the clear definition of requirements right from the get-go makes the development process way more predictable and enhances your code's resiliency against future changes. In summary, we've just dived into the essential components of the red-green refactor workflow. This structured approach to software development doesn't just boost your productivity, it really nurtures a coding discipline that, over time, leads to long-lasting quality. By sticking to this cycle, you're not only ensuring that your code works, but that it works well. It becomes manageable, adaptable, and honestly, something you can seamlessly build upon in the future. Now, as we move forward in this coding journey, keep those core principles of the red-green refactor workflow front and center in your practice. Embrace the spirit of iterative refinement, and most importantly, enjoy the process of crafting streamlined, efficient, and high-quality software. By diving deep into the essential techniques of test-driven development, focusing on writing a failing test using the Vitest test runner. By understanding how to lay the groundwork for our tests, we can drastically enhance the reliability and maintainability of our code. So far, we've explored the red-green refactor workflow in test-driven development, particularly in building a birthday list component in Svelte. We went through those 3 critical phases: writing failing tests, what we call red, ensuring they pass, or green, and then refining our code, which is the refactor step. Now, as we move forward, we're really going to dig into that all-important phase of writing the failing test. So let's kick this off by chatting about the crucial role of testing in modern software development. Writing a failing test might sound a bit counterintuitive, right? I mean, why on earth would we want to write a test that doesn't pass? The beauty of test-driven development is that it allows us to verify the functionality of features before we even start coding them. It's a method that makes sure you're building to requirements while keeping you from the temptation to write unnecessary code. By starting out with a failing test, you're clearly defining what your code should achieve. And trust me, coding without a clear specification can lead to all sorts of assumptions and vague expectations, often ending in frustration down the line. So let's embrace this process and watch how it transforms our coding experience. Next, we'll dive into setting up our test using the Vitest test runner. First things first, let's import the essentials. We need describe, it, and expect from Vitest alongside render and screen from the Svelte testing library. Now, why is this importation so crucial? Well, it paves the way for us to organize our tests and effectively assert outcomes. All right, moving on. Let's kick off our test suite with that describe function. It's perfect for grouping related tests together. Inside this suite, we're going to use it to specify what our particular test will verify. And guess what? We're targeting the birthday component to ensure it accurately displays a person's name. So here's the fun part. In the body of our test, we're going to utilize the render function, mounting our birthday component with the prop name set to Hercules. This setup gets everything ready for us to inspect. Now, to check if our component is rendering Hercules properly, we'll employ screen.queryByText, which will look through the rendered output for that specific name. And here's the kicker. We'll then assert its visibility using expect. This means if Hercules isn't found, our test will fail. And you know what? That initial failure, it's actually a stepping stone. It guides us as we create our functional component, solidifying our understanding of what we're aiming for. Now, let's take a moment to break down the significance of writing this failing test. The test serves not merely as a check, but as a living documentation of how your component should behave. This means that later, any developer looking at your code will immediately understand that the component is expected to render a name due to this very test. Think of it as a contract with the future. Every line you write today is a promise to deliver functionality that works as outlined. Moreover, this practice fosters confidence in our codebase. As we continue building our application, we can rest assured that if someone, including future you, modifies the component, the tests will catch any deviations from the intended behavior. With this philosophy at the core of your development process, every piece of code you write becomes part of a robust framework to catch errors early in development. In this scenario, we're setting ourselves up with the perfect failing test to indicate whether we'll succeed or not. Now, let's dive into how we can implement the birthday component to meet the requirements we defined earlier for our test, shall we? The first part of our code features a script tag where we declare a variable using the export keyword. This is super important because it lets us pass the name variable as a prop when the component gets invoked, which means it's really versatile for different contexts where we might want to use this component. Now, after the script, we have the HTML structure that will ultimately display the name. Here, we wrap the name variable inside a span tag. This is a common HTML element that allows us to style or emphasize pieces of text without messing with the layout. To really make that name pop, we nest it within a strong tag, which semantically tells browsers and users alike that this text is important. By using this simple yet effective structure, we maintain clarity and focus within the component while ensuring it meets the specifications laid out in our test. It's all about striking that perfect balance between performance and usability, right? We want to adhere to the principles of clean code, which is really our goal as we build this application iteratively. This progression showcases the initial effectiveness of the red-green refactor approach. By starting with a failing test, we provide a clear path toward a working solution. But, what if we never quite understood what our test was supposed to validate, or if we stumbled onto some assumptions about the component's behavior? A failing test crystallizes the expectations and creates a tangible goal for developers to aim toward. This is why the act of writing a failing test is so foundational. It establishes a benchmark for success that drives the subsequent development work. Now, as we develop further functionality, we can build upon this solid groundwork with confidence, knowing that every component is well-defined and well-tested. Each failing test we confront is not a barrier. Rather, it's an invitation to refine our understanding of how components should work together. This method directs our coding efforts systematically, leading to a well-organized and clear software architecture. Now that you're armed with a clear understanding of writing a failing test, let's take a moment to dive a bit deeper. You should notice that this methodology goes beyond just creating components. It's really all about establishing a broader principle of working in iterations. By applying concise practices, we can verify that each feature does what it's supposed to do. Writing failing tests, it forces you to draw clear boundaries around your goals, illustrating precisely what each part of your application is meant to do. This creates a much cleaner and more fault-tolerant environment for coding. So, to wrap it up, writing a failing test isn't just a practice, it's a mindset. It enables us to learn and iteratively build with intention. The goals of our tests, they should guide us right back to our code. Instead of jumping in with those expectations and assumptions, we equip ourselves with clear criteria for behavior. And as we've seen, this approach benefits not only our current development efforts, but also serves as a valuable resource for anyone who interacts with our code in the future. So here's a little reminder. The next time you feel tempted to just dive straight into coding a new feature, pause for a moment. Take a second to sketch out what the expected functionality should look like in terms of a test. It's one of the simplest changes you can make to your approach, and let me tell you, it will yield some of the most significant benefits for your development experience. Happy coding!
Now let's implement the following code to create a dynamic product page in SvelteKit. We start by defining a load function inside a script context equals module tag. This function is essential as it is automatically called whenever a user navigates to the relevant route. Within this function, we extract the product ID from the URL parameters, allowing us to fetch data specific to the product being requested. Next, we make an asynchronous fetch call to an API endpoint that provides product details based on the product ID. We then check if the response from the API is successful. If it is, we return the product data as props, which makes it accessible inside the component. However, if the response fails, we return an error status and a message to gracefully handle any issues that might arise during the data retrieval process. In the second script block, we export the product variable to be utilized in our HTML structure. This allows us to display the product title, image, description, and price directly on the page. By implementing these functions, we ensure a smooth user experience by preloading all necessary data before rendering the component. Now let's see how we can implement the load function to fetch product data dynamically using SvelteKit's routing capabilities. We begin by defining the function inside a script context equals module, which allows it to be called whenever a user navigates to the corresponding product URL. The function extracts the product ID from the URL parameters, enabling us to make a targeted API call to fetch the relevant product data. As we handle the fetch request, it's crucial to check the response status with "OK". If the request fails, we can return an error with an appropriate status code, which allows for graceful error handling later in our component. If the fetch is successful, we pause the JSON response and pass the product data as props to our component. Next, in the main script tag, we export the product and error variables. This allows us to handle errors intelligently within the UI. Using Svelte's reactive syntax, we introduce conditional rendering to display either the product details or an error message. This ensures that users receive clear feedback when issues arise, significantly enhancing the overall user experience. Next, we will implement a loading state to enhance user experience while we fetch data. In the SvelteKit component, we introduce a loading variable initialized to true, signifying that our product data is still being acquired. Once the product is successfully retrieved, this flag is set to false, indicating to the application that data is ready to be displayed. In the render block, we utilize Svelte's reactive syntax to handle different states. We check if there is an error during data fetching first and display an appropriate error message if so. If there is no error, we then assess the loading state. While the data is still being retrieved, users will see a loading message rather than a blank screen. This effectively prevents confusion during the data loading process, allowing users to remain informed about what's happening. Finally, once the product data is available, the appropriate details, such as the title, image, description, and price, are rendered for the user. This approach significantly improves the perceived performance of the application by providing clear visual feedback throughout the data fetching process. Now let's see how we can implement a dynamic loading function in our SvelteKit application. We start by defining a load function within a script context equals module tag. This function takes the params object, allowing us to extract the productid directly from the URL. With this identifier, we can make an API call to fetch the product details from a placeholder API. Next, we use the fetch method to retrieve the product data. It's important to check if the response is successful. If not, we return an error status along with a descriptive error message. When the fetch is successful, we pause the JSON data and return it as props, making the product information available for our Svelte component. This structure ensures that when a user navigates to a specific product page, they receive prefetched data ready for display, significantly enhancing the loading experience. As a result, users see the product details immediately, rather than waiting for the JavaScript to execute, improving the overall performance and user engagement. This implementation is a fundamental aspect of SvelteKit's server-side rendering capabilities, exemplifying how we efficiently manage dynamic data in a client-friendly way. Now let's implement the following code to handle loading reviews for a specific product. In the SvelteKit root file located at src/root/products/product-id/reviews, Svelte, we start with a module script that exports an asynchronous load function. This function takes in the params object, which includes the productid extracted from the URL, allowing us to dynamically fetch reviews based on the selected product. Next, we make a fetch call to the mock API endpoint using the productid. After sending the request, we check if the response is okay. If the response indicates an error, we return an object with the error status and a brief message. When the fetch is successful, we convert the response data to JSON format and return it as props, providing the reviews data to our component. Below the module script, we have another script that exports the reviews variable. This variable allows us to access the fetched reviews within our main component. In the main section of the file, we display the reviews using an unordered list. By iterating over the reviews, we create a list item for each review, showcasing the comment and rating, thus enhancing the user experience by presenting pertinent feedback about the product. Now, let's take a look at how we can implement tests for our SvelteKit product page component. We start by importing the necessary functions from the testing library and our product page component from its designated file. The main testing structure utilizes the describe function to group all our related test cases under the product page. Next, we define individual test cases with the it function. The first case asserts that the product title renders correctly by using the render function, which simulates rendering the product page component with predefined product props. This allows us to check if the title is present in the document. We follow a similar approach for the subsequent tests, verifying that the product description, price, and image are displayed correctly. Each of these tests is structured to ensure that the relevant details populate the page as expected, yielding accurate user-facing information. Lastly, as we expand our component, like adding a Buy Now button, we also include additional tests for user interactions. For example, we simulate clicking the button, checking that the alert triggers correctly, reinforcing the importance of usability in our components. This comprehensive test suite ensures that our product page behaves correctly across different conditions, supporting robust application performance. Now, let's implement the structure of our product page component. At the beginning of the component, we declare a script tag that exports the product variable, which is passed in as a prop. This allows our component to receive product details dynamically. Next, we define the main content within a main tag. Inside this section, we utilize Svelte's reactivity by directly binding the product data to the template. The product title is presented in an H1 element, providing a clear and prominent display. We then include an img tag to show the product image, ensuring that it uses the product image source with an appropriate alt description to improve accessibility. Following the image, we have two p tags, one for the product description and another for the price. The price is formatted to include a $sign for clarity. This structure not only showcases essential product information, but also leverages Svelte's strengths in creating reactive UIs by using props efficiently. After we write this component, we can run our tests again to confirm they pass, demonstrating that we have implemented the required functionality to meet the predefined expectations. Now let's see how we can implement interaction testing for our product page component by adding a Buy Now button. This button, when clicked, triggers an alert that confirms the purchase with the message Purchased. To capture this interaction in our tests, we begin by utilizing the FireEventClick method, which simulates user clicks on DOM elements. In our test suite, we first render the product page, component, and pass in a sample product object as props. This allows us to mimic the component's behavior in a real-world scenario. After rendering, we retrieve the button element using getByText to ensure we are interacting with the correct element. Next, we mock the alert function using Jest's spying capabilities, which lets us track its calls without actually displaying the alert. Once we simulate the button click, we utilize an assertion to check that the mock alert was called with the expected message. Finally, it's crucial to restore the original alert function to maintain the integrity of our tests. This entire setup confirms that our component behaves correctly in response to user interactions, reinforcing the importance of testing not just the rendering of data, but also how users engage with the application. Now, let's implement the conditional rendering for displaying a discounted price on the product page. In our code, we introduce an if block, which is a Svelte-specific syntax that allows us to render a section of the template conditionally based on the truthiness of a specific expression. Here, we are checking if the product discounted price exists. If product discounted price is truthy, meaning there is a discount available, we render a paragraph element that showcases the discounted price. Within this paragraph, we use strong tags to emphasize the discounted price for better visibility. This approach enhances the user's understanding of pricing, especially beneficial for products on sale. By leveraging Svelte's reactivity, the display updates immediately if the discounted price changes. It's important to ensure that your associated tests are also updated to account for this new feature. This way, we can verify that our component correctly reflects pricing changes when the product data is updated. Thus, maintaining a well-aligned test suite ensures our application remains robust as we evolve the component's features. Next, we will implement error handling within our product page component. The component receives two props, product and error. By checking if an error exists, we can gracefully handle loading issues. If an error is detected, the component throws a new error, signaling that the product could not be loaded. This pattern allows us to inform users proactively about potential issues, maintaining a positive user experience even in adverse situations. Now, let's see how we can implement a test for this error scenario. We will simulate an error state by using the render function from our testing library. In our test, we pass in an error prop simulating a loading failure. This test checks if the user interface responds correctly to the error by expecting to see the relevant error message rendered on the page. Such proactive tests ensure that our application remains reliable and user-friendly under all conditions. confirming that our UI can handle mistakes gracefully, which is essential for maintaining trust with our users. As we develop our application further, consider incorporating coverage reports to gauge how much of your codebase is covered by tests. Tools like Istanbul and Nick offer great support to track code coverage statistics for your unit tests. This insight can help you identify areas that are under-tested, guiding you to maintain a high-quality application with fewer bugs. Monitoring code coverage lets you refine your testing strategy continuously. After all, the goal of TDD isn't just to write tests, but to foster better application design and reliability, resulting in fewer surprises down the road. In summary, we've taken significant strides in understanding how to apply TDD effectively to our SvelteKit page components. By beginning with clear tests and then building the corresponding code, we ensured every piece fit together seamlessly. To wrap things up, remember that every test serves as documentation of your app's features. Whenever you revisit your code or share it with fellow developers, they'll have a clear view of expected behaviors and interactions, broadening collaboration and enhancing overall code quality. Now, in our next session, we'll dive into more advanced routing techniques, including dynamic parameters and authentication strategies to secure our routes. Thank you for joining this session on test driving your page component in SvelteKit. I look forward to seeing you in our In this tutorial, we're going to dive deep into the intriguing world of SvelteKit forms, focusing on how to effectively test drive them. We'll explore topics such as adding Playwright tests, creating form components, and implementing form actions in SvelteKit. Grab your coding gear because this is going to be exciting. So far, we learned about the importance of creating a well-defined page component in SvelteKit and how to apply test-driven development, TDD, to ensure it behaves as expected. We started by writing tests for rendering a product page and then implemented the corresponding component, validating its functionality through tests. Additionally, we explored the significance of maintaining tests as the component evolves, which includes handling errors and adding new features. Now, we will cover how to test-drivenly create forms in SvelteKit, enabling us to handle user inputs efficiently. Now let's take a look at how we can implement a Playwright test to save a new birthday in our application. This test initiates by navigating to the birthdays route, ensuring that we are in the correct context of our application. It then locates the input fields for name and date of birth using their accessible labels and fills them with the appropriate test data, in this case, Persephone for the name and 1980-50101 for the date. After populating the fields, the test simulates a click on the Save button, which triggers the form submission process. Following this action, the test includes an assertion to check if the name, Persephone, is visible on the page. This assertion is crucial as it confirms that the user interface dynamically updates to reflect the new entry, thereby validating that our form submission works as intended. Through this test, we gain confidence that our form not only accepts the inputs, but also reacts correctly to user interactions, encapsulating a key aspect of end-to-end testing in Playwright. Now let's take a look at how we can implement our form component in Svelte. We begin by creating a basic HTML structure within a form element where we specify the fields necessary for user input, the name and date of birth. Each input field is wrapped in a label, which enhances accessibility by giving users clear identifiers for what information is required. The form also has a submit button labeled Save, which will trigger the form submission when clicked. Next, we need to ensure that our form behaves as expected, so we will write a test to verify that the form renders correctly on the page. This test checks for the visibility of the form using the render function from our testing library, confirming that it appears properly when the component is loaded. By using the query by role method, we can specifically target the form role, allowing us to accurately determine if it is displayed to users as intended. This step solidifies the foundation of our form, ensuring that we can move forward with confidence as we enhance its functionality. Now that we have our form set up, let's implement the handling of data submission through form actions in SvelteKit. The code begins by exporting an object named Actions, which is crucial for processing form submissions. Within this object, we define a default asynchronous function that takes a request parameter. This parameter is representative of the incoming request that includes the data submitted by the user. Next, we utilize the requestFormData method, which enables us to extract the data from the form once it has been submitted. This is an important step as it allows us to access the user input in a structured way. Here, we have a placeholder comment indicating where we will process the form data. In a practical application, this is where we would add logic to handle the data, such as validating it or storing it in a database. This setup prepares the foundation for how we will handle incoming data, ensuring that during the user's action of submitting the form, we can efficiently process their input. This structured approach not only enhances the functionality of our application, but aligns well with the principles of test-driven development, making our code more reliable. Now let's implement a utility function to simulate form data for our tests. The CreateFormDataFromObject function utilizes the FormData API to create a new FormData instance, which closely mimics how data is structured when submitted through a form in SvelteKit. By looping through the keys of the input object, it appends each key value pair to the FormData instance. This function is essential for preparing our simulated requests during testing, ensuring that we can accurately represent user input and validate our actions seamlessly. Next, we will set up a Vitest test suite for the form's actions. The test describes the behavior of the default action associated with our birthdays route. In this suite, we'll create a simulated request using our utility function, passing it a name and date of birth as parameters. After calling the action with this request, we use an assertion to check whether the expected birthday data is properly added to the application state. This step is crucial as it confirms that the transition from form submission to data handling works flawlessly, reinforcing the reliability of our implementation in real-time scenarios. Now let's implement the following functionality to manage our birthday entries. We start by initializing a simple database using an array named db, which will temporarily hold the birthday data. Next, we define the addNew function that takes an item as an argument and pushes it into this array, allowing us to store incoming birthday details. Now let's take a look at how we will craft our form action. In the Actions object, we define a default function that is asynchronous, allowing us to handle the form submission effectively. Inside this function, we first await the requestFormData method to retrieve the submitted data in a suitable format. Following this, we call the addNew function and pass it an object containing the user's input. We gather the name and date of birth from the form data using data.get, ensuring we store all relevant information in our makeshift database. This structure not only captures user input, but also simplifies data management within our application, paving the way for later retrieval and display of birthdays. To summarize, we've successfully navigated the intricacies of SvelteKit forms. We started by setting up a Playwright test to verify user inputs into our form, progressed to creating the essential form component, and concluded by implementing and testing the form action in SvelteKit. Each of these steps provides crucial insights into handling forms in a user-centric way while ensuring reliability and validity using test-driven development. As you now put this into practice, remember that testing isn't just about ensuring the present functionality works, but also about preparing your code for future changes, keeping it flexible and robust as your application evolves. In our next session, we will dive into advanced routing techniques, including dynamic parameters and authentication strategies, enhancing the capabilities of our SvelteKit application even further. So stay tuned. In this segment, we're going to discuss something crucial in SvelteKit, implementing form actions. The form action is the thing that SvelteKit calls when the form is submitted. This fundamental feature enables dynamic interaction in your applications, allowing you to handle user input effectively. So far, we learned about implementing Playwright tests for SvelteKit forms and creating a form component to collect user input. We explored testing the form's display and how to handle form submissions using SvelteKit's form actions. Additionally, we set up an action to process incoming data, ensuring that user inputs are properly stored. Moving forward, we'll delve deeper into a detailed walkthrough of creating, implementing, and testing form actions in SvelteKit. Now let's take a look at how we can define our form action in SvelteKit by creating a plus page server.js file. In this file, we export an actions object that includes a method called default. This method is crucial because it gets invoked automatically when the associated form is submitted. Inside this method, we utilize await request form data to retrieve the data submitted through the form as a form data object, allowing for easy access to input fields. We can extract the values of specific fields using the get method, which is demonstrated by capturing the name and date of birth. This not only logs the values to the console, but also sets the stage for further processing, such as saving the data to a database. Lastly, the method returns a response indicating whether the operation was successful, thus providing a clean and efficient way to handle form submissions and manage incoming data within our application. Now let's see how we can implement the form that will interact with our defined action in SvelteKit. We create a form element with the method attribute set to post, indicating that we wish to send data securely without exposing it in the URL. The action attribute points to the specific form action that we've designated in our plus page server.js file, enabling SvelteKit to route the data appropriately upon submission. Inside the form, we have labels and input fields for the user's name and date of birth, both marked as required to ensure that the form cannot be submitted without these fields being filled out. The button with the type Submit triggers the form submission. When the user clicks this button, SvelteKit collects the input data and forwards it to the server, where it can be processed by the corresponding action we defined earlier. This setup allows for a seamless user experience, facilitating the handling of user input effectively while maintaining the integrity of the data sent to the server. Now let's implement the following action in our SvelteKit application to provide user feedback during form submissions. In this function, we define a default action that listens for incoming requests after the form is submitted. The first step is to retrieve the form data using request form data, which allows us to access the individual fields submitted by the user. Next, we extract the name and fields from the form data. It's crucial to validate this input. Thus, we introduce a conditional check to verify if either the name or date of birth is missing. If any required field is missing, we return an object indicating failure, along with a descriptive error message. This way, users are promptly informed of what went wrong. If both fields are present, we log the user's input to the console, demonstrating how the data can be processed further, such as saving it to a database. Finally, the action responds with a success message, which can be utilized to confirm successful form submission to the user, enhancing the overall user experience. This feedback loop is essential in creating a responsive and interactive application. Now let's implement the following form in our Svelte component to handle user inputs effectively. The form provides a structured way to collect user data, including a text field for the user's name and a date field for their date of birth. Each input is marked as required, ensuring that users cannot submit the form without providing the necessary information. To give users immediate feedback on their submission, we utilize Svelte's reactive properties. After the form is submitted, we check for the success condition. If the submission is successful, a confirmation message is displayed to the user. On the other hand, if there is an error, we show an error message in red text, which ensures that users receive clear and immediate visual cues about the outcome of their submission. This approach not only enhances the user experience, but also ensures that they are well informed about their form submission status. Overall, this structure enables us to gather input seamlessly and provides essential feedback to enrich user interaction within our Svelte application. Now let's take a look at how we handle user input within the defined form action in SvelteKit. In our action, we first retrieve the submitted form data using the await request form data method, which gives us access to a form data object. This object allows us to conveniently extract values from the form fields by using the get method. For instance, we retrieve the user's name and date of birth from the form using their respective field names. Next, we implement a validation check to ensure that both fields are filled in. If either of the fields is missing, we return an object indicating failure and provide an appropriate error message. This is essential for guiding users to complete the form correctly, enhancing their experience. On successful validation, we proceed to log the values we've captured, simulating a processing step where this information could be saved to a database or used further. Finally, we send back a success message to confirm to the user that their submission was processed successfully, completing the action cycle. This structured approach ensures that the form actions are both efficient and user-friendly. Now let's see how we can implement multiple form actions in our plus page, server.js file. To effectively manage separate forms on a single page, we define unique action names within an exported actions object. Each action corresponds to a distinct form submission, enabling SvelteKit to identify and process the submitted data correctly. In this example, we have two actions, save birthday and save event, each defined as an asynchronous function that receives the request object. These functions will handle the incoming form data when a user submits a form. Within each action, you can implement the logic to process the form data appropriately, such as saving it to a database or performing other business logic. This modular approach helps to keep your form handling organized, especially when working with multiple forms that may require different data handling strategies. Now let's take a look at how to structure the forms that correspond to these actions. Each form will specify its action name in the action attribute of the form tag, ensuring that upon submission, the correct action is invoked. This approach not only clarifies the data flow, but also allows for a seamless user experience as submissions are routed to their respective handlers. Next, we will write a Playwright test to ensure our form action works as intended. This test will simulate the process of filling out the form and submitting it to verify the expected response. We start by launching a Chromium browser instance using Playwright's synchronous API. Then, we create a new browser context and open a new page to navigate to the form's endpoint. Now, let's see how we can fill out the form. We use the pageFill method to enter a name and a date of birth into the respective input fields. After populating these fields, we simulate a click on the Submit button using PageClick. This action triggers the form submission process. To confirm that our form action executes correctly, we assert that a success message appears on the page. The test checks for the visibility of a specific text, indicating that the form was submitted successfully. Finally, we close the context and the browser instance to tidy up after our test run. This step ensures that the test not only simulates user behavior, but also validates the functionality of our form submission within the SvelteKit application. By diving into implementing form actions with SvelteKit today, we covered significant ground on handling user input efficiently. We explored how to define form actions, connect them to forms, provide feedback to users, and ensure we handle errors correctly. We even touched on how to test our form submissions using Playwright to ensure everything is working as intended. As you build your applications, remember the importance of clear feedback and proper handling of data to create an engaging user experience. With form actions, you can streamline interactions in your SvelteKit applications considerably. In future segments, we will expand our knowledge by tackling advanced routing techniques to enhance the capability of our applications even further. Now that our system is accepting new birthdays, we need to validate the data coming in. Form validation is critical in web development, ensuring that the information collected from users is correct, complete, and suitable for processing. It helps prevent errors and enhances the user experience. Let's explore the principles of form validation, the techniques you can implement in SvelteKit, and how to test them effectively. Now, let's implement the following function to validate the birthday input in the format YYYYMMDD. The validate birthday function begins by defining a regular expression pattern that specifies the expected format. This pattern uses \d4 to match 4 digits for the year, followed by 2 digits for the month, another, and finally 2 digits for the day. We use the ray_match function to check if the provided birthday string conforms to this pattern. If it matches, the function will return true, indicating valid format, otherwise it will return false. This function serves as an essential part of our form validation process, ensuring that users enter their birthdays in the correct format before data submission. By catching format errors early, we can greatly enhance the user experience and prevent incorrect data from being submitted, which would require additional handling and error messaging later in the process. Integrating this function into our application allows us to maintain data integrity and ensures that the backend receives data that meets our specified requirements. Next, we will enhance our birthday validation function to ensure the input not only conforms to the correct format, but is also a logical and valid date. In the new implementation, we first define a regular expression pattern to check the format YYYYMMDD. If the input matches this pattern, we then use the DataTime module to attempt to convert the string into a DataTime object. This conversion is crucial as it automatically handles various date validations for us, including leap years. If the conversion is successful, we perform a critical check to ensure that the date does not fall in the future by comparing it with the current date and time. If the date exceeds the present moment, the function returns a message stating that the date cannot be in the future. Additionally, if the date conversion fails, we catch the resulting value error and return a distinct message informing the user that the input date is invalid. If the input does not match the format in the first place, we return a message indicating that the format is incorrect. This feedback ensures that users receive precise information to correct their input, enhancing their overall experience. Now let's implement the following form for entering a birthday. This form utilizes the Svelte framework to enhance user experience through real-time validation. We start by creating a form element with an onSubmit_prevent_default=handle_submit attribute, which prevents the default form submission behavior to allow us to handle the submission programmatically. Inside the form, there's a label prompting the user to enter their birthday, followed by an input element of type date. This choice leverages modern browsers' built-in date picker for better usability. To ensure that users provide valid input, we specify the required attribute, mandating that this field must be filled out before submission. Additionally, the max attribute is dynamically set to the current date, ensuring that users cannot select a future date, thereby enforcing logical constraints on the input. The pattern attribute implements a regular expression that defines the expected format for the date, which is YYYYMMDD. This provides immediate feedback for formatting errors before the form is even submitted. Finally, a submit button is included, enabling users to send their input for further processing. Next, we will implement server-side validation for the birthday input to ensure its integrity before processing. In our handle birthday submission function, we first retrieve the form data and specifically extract the birthday field. This step is crucial as we want to verify the user's input directly from the form submission. Now let's see how we can validate this birthday input. We call the validateBirthday function, which checks whether the input adheres to our predefined criteria. This function returns two values, a Boolean indicating the validity of the date and a message providing feedback. If the birthday is not valid, we return a response with a 400 status code, along with an error message, to inform the user about the nature of the issue. On the other hand, if the validation is successful, we proceed to process the birthday, such as saving it to a database. We then return a positive response with a 200 status code and a success message, confirming that the birthday submission was successful. This two-step validation process enhances security and user experience, ensuring only valid data is processed. Now let's see how we can handle data storage securely using SQL Alchemy, an ORM for Python. The first line of the code imports the necessary components from SQL Alchemy, including Create Engine, which allows us to set up the database connection, and Session Maker, which is used to create a new session for interacting with the database. Next, we establish a connection to our SQLite database with Create Engine, specifying the database file. This engine acts as the starting point for our database operations. We then utilize the Session Maker to create a session object, which we use to manage our interactions with the database. Now let's implement a function called addUser, which will be responsible for adding a new user to our database. Within this function, we first create a new instance of the user model, passing in the user's birthday as an argument. This instance represents the new record we want to add. After that, we use the session to add the new user to our database and commit the transaction, which finalizes the changes. This method encapsulates best practices for safely interacting with a database and significantly reduces the risks of SQL injection attacks, as SQL Alchemy automatically handles parameterization for us. To wrap everything up, always provide meaningful user feedback. Whether validation fails on the client side or server side, ensure that your users understand what went wrong and how to correct it. This approach not only improves user experience, but also reduces frustration. In our previous examples upon input checks, instead of generic error messages like invalid input, give specific, actionable messages like date cannot be in the future. In conclusion, form validation is a multifaceted process that includes checking input formats, validating data logic, implementing both client-side and server-side validations, securing against attacks, and providing clear feedback. These principles, when applied effectively, enhance data integrity and user experience significantly. Understanding and implementing these principles prepares you to build robust forms that can handle user input efficiently and safely. Thank you for tuning in. Now, let's apply what we've learned and see how we can test our form validations using Playwright in. Next, we'll implement the server-side action in the plus page, server.js file to handle form submissions. In this code, we define an asynchronous function called submitForm, which takes the incoming request as its argument. This function utilizes the requestFormData method to access the submitted form inputs, allowing us to retrieve the birthday field. Once we have the birthday input, it's crucial to validate that this data is correct and meets our criteria. Now, we will incorporate validation logic that we've previously discussed. If the validation fails, we can return a 400 status code accompanied by an error message indicating the specific issue with the input. This ensures that the user is promptly informed of any errors and can make the necessary corrections. On the other hand, if the input passes our validation checks, we can proceed with processing the valid birthday data, potentially by saving it to a database or performing further operations. Finally, we will return a 200 status code with a success message to acknowledge that the submission was successful, thereby completing the server-side form validation process effectively. Now let's implement a validation function for the birthday input. In our validation.js file, we define the validateBirthday function that checks if the input matches a specific date format using a regular expression. This ensures the user enters the date in the expected YYYYMMDD format. If the input fails this check, the function returns an object with a valid property set to false and an appropriate error message. Next, we create a date object from the input and compare it with the current date to ensure the birthday is not set in the future, returning another error message if it is. Additionally, we check if the date object generated from the input is valid by using the getTime method. If the date is invalid, we relay this back as well. Only when the input passes all these checks do we return an object signifying the input is valid. Now let's see how we can incorporate this validation function into our server-side action in the plus page, server.js file. Here, we are importing validateBirthday and using it within the submitForm action to validate the birthday received from the form. If validation fails, a 400 status with an error message is returned, ensuring we guide the user feedback effectively. If validation is successful, the form submission is processed with a success message. Now let's see how we can implement a form to capture user birthday input and provide immediate feedback in case of errors. We start by setting up a simple HTML form that includes a date input for the user to enter their birthday. This input is required to ensure that the user provides their birth date before submitting the form. The form also includes a submit button to trigger the submission process. Next, we introduce a conditional block within the form that displays an error message when the error variable is populated. This variable is crucial as it allows us to provide instant feedback to the user if their submission encounters any issues. By effectively utilizing this error messaging system, we enhance the user's experience by clearly indicating what went wrong during the submission process. Now let's take a look at the handle submit function, which is invoked when the form is submitted. In this function, we perform an asynchronous fetch request to send the user input to the server. After receiving the server's response, we check if the submission was successful. If an error occurred, we assign the corresponding error message to the error variable. Otherwise, we clear the error and may display a success message to the user. This implementation ensures that users receive timely feedback, making the form experience more user-friendly. Next, we will implement the server-side handling for user input by connecting to our database using SQL Alchemy. In the code, we begin by importing the necessary components from SQL Alchemy, including Create Engine for establishing the database connection and Session Maker for creating sessions to interact with the database. We also import our user model, which represents the database schema for users. Now, let's define our database URL, which specifies the connection string to our SQLite database. Using Create Engine, we create an engine instance that serves as a communication interface between our application and the database. We then set up the session through Session Maker, binding it to our engine, allowing us to perform database operations smoothly. Next, we write the function addUser, which accepts a birthday as input. Inside this function, we establish a session by calling session, create a new user instance with the provided birthday, and use the session to add this new user to the database. Finally, we commit the session to save the new user's data. This way, we ensure that the input is processed securely and efficiently, exemplifying the benefits of employing an ORM for data submission. Now let's see how we can enhance our submit form method with robust error handling to improve user experience and application stability. We start by wrapping our logic inside a try-catch block. This allows us to catch any unexpected errors that may arise during the execution of our code, such as issues encountered while connecting to a database. If an error does occur, instead of crashing, we return a status code of 500 alongside a generic error message. This approach provides users with meaningful feedback without exposing sensitive details that could be exploited. Next, we validate the birthday input using the validateBirthday function we defined earlier. If the input is invalid, we respond with a 400 status and an error message, informing the user what went wrong. When validation passes, we proceed to invoke the addUser function to store the user's birthday. Finally, upon successful submission, a 200 status is returned along with a success message indicating the birthday was submitted successfully. This structured handling of input, validation, and error management leads to a more resilient application, ensuring that we not only safeguard our data, but also maintain a positive user experience. To summarize, implementing server-side validation is about ensuring that the data received on the server meets all requirements and is safe to process. This involves first capturing the user's data, validating it through meticulously crafted functions, providing user feedback on errors, sanitizing inputs to mitigate security risks, and employing error handling to manage unforeseen issues. And as much as we love a good joke, security and integrity in user input is no laughing matter. Now that we've covered server-side form validation implementation, we will next explore how we can test these form validations using Playwright, ensuring that our application runs smoothly and reliably in real-world scenarios. Not only will we ensure our validations work correctly, but we'll also dive into automated testing practices as we raise the quality of our software development process. Get ready for some exciting testing adventures. In this tutorial, we're diving into updating form actions to handle edits, a crucial improvement for any web application that manages data. When users want to update their information, it shouldn't feel like a cumbersome process. Instead, a smooth and intuitive experience is essential to retain user engagement. So far, we covered the importance of server-side form validation, methods for validating inputs, error handling, security measures against threats like SQL injection, and utilizing ORM for safer database interactions. Now, we will talk about updating our form actions to handle edits and ultimately enhance user experience by allowing changes to existing entries, like updating birthdays. Now let's take a look at the structure of our form, which is crucial for both adding and editing birthday entries. The form is set up to send data via a POST request to the /API/birthdays endpoint, ensuring that user inputs for names and birthdays are collected. The method attribute specifies that the data will be sent to the server when the user submits the form. Each input field is accompanied by a corresponding label to enhance accessibility, guiding users in providing their information. The name and birthday inputs are marked as required, ensuring that users cannot submit the form without filling in these crucial fields. Next, we will modify the form to accommodate edits by dynamically changing its action attribute based on the presence of an id. This means that if an entry is being edited, the form's action will point to the specific resource using the id. We also incorporate the current values of the name and birthday inputs into the form fields when editing, offering a seamless experience for the user. Finally, we will update the Submit button's label to reflect the action being taken, using Update Birthday for updates and Add Birthday for new entries, enhancing clarity for the user regarding their actions on the form. Now let's take a look at how we modify our form to accommodate both creating new entries and updating existing ones. This begins by dynamically setting the form's action attribute based on the presence of an id. If the id exists, the action becomes a PUT request, targeting the specific birthday record with the corresponding endpoint. Conversely, if there's no ID, it defaults to a POST request for creating a new birthday entry. Next, we will implement input fields for the name and birthday, ensuring that they are required for valid submission. Both fields use the value prop to prefill existing data when editing, enhancing user experience by allowing seamless updates without extra steps. Furthermore, the Submit button dynamically adjusts its label based on whether the form is editing or adding a new entry. It displays Update Birthday for existing records and Add Birthday for new ones. This conditional rendering not only clarifies user intent, but also simplifies the process by providing appropriate feedback through button text, ensuring that users understand which action they are about to take. Overall, this strategic approach improves the overall functionality of your birthday management web application. Next, we will write the following server-side code to handle the incoming requests for creating and updating birthday entries. This is achieved by defining two functions, one for handling POST requests and another for PUT requests. In the POST function, we start by pausing the request body to extract the name and birthday. This data is then used to create a new birthday entry in the database through an asynchronous call to db birthdays create. Upon successful creation, the new entry is returned in JSON format, allowing the client to receive a confirmation of the addition. Now let's take a look at the PUT function, which is designed for updating existing entries. Here, we again pause the request body for the name and birthday, but we also retrieve the id from the URL parameters to identify which entry to update. The db birthdays update method is called, where we specify the entry to be modified along with the new data. Once the update is successful, the modified entry is sent back to the client as a JSON response, keeping the data flow clean and understandable. This structured approach enhances code organization, making it easier to maintain and scale. Now let's take a look at how to test our API endpoints using curl commands. First, we will add a birthday entry by sending a post request to our server. This command sets the request type to post, targets the endpoint for adding birthdays, and specifies the content type as JSON. The data payload contains the name and birthday of the individual, formatted in JSON. This request will help us verify that when we submit a birthday, our server correctly captures the information and stores it in the database. Next, we will see how to update an existing birthday by implementing a put request. This command is similar to the previous one, but instead of creating a new entry, it updates an existing one identified by the ID provided in the URL. Again, we specify the content type and the updated data in JSON format. By running this command, we can check if our server successfully processes the update and ensures the changes are accurately reflected in the database. Utilizing these curl commands allows us to validate the full functionality of our API before proceeding to automated tests with tools like Playwright. Now let's take a look at how we handle form submissions with the necessary feedback for the user. We define a variable called message to store the feedback message that will be displayed after form submission. The handle submit function is triggered when the form is submitted, where we first prevent the default submission behavior from refreshing the page. Next, we check if an id exists to determine whether we are updating an existing entry or creating a new one. Depending on this condition, we make an asynchronous fetch request to either update the birthday with a put request or add a new birthday with a post request. The relevant data is sent in a JSON format with the user's name and birthday. Once a response is received, we check if the operation was successful by evaluating response OK. If it is, we assign a success message to the message variable that signifies whether the birthday was updated or added successfully. In the event of an error, we set the message to inform the user of the issue. This approach ensures users receive immediate feedback on their actions, enhancing their overall experience with the application. Now let's see how we can implement the testing framework using Microsoft Playwright to ensure our application functions as expected when adding and editing birthdays. First, we'll need to install Playwright in our project using npm, which will set up the necessary dependencies for browser automation. This installation allows us to leverage Playwright's powerful capabilities to simulate user interactions within our application effectively. Next, we'll write a testing script that opens a browser and navigates to our application's homepage. In this part, we will begin by simulating a user filling out the birthday form for the first test case. The script fills in the name and birthday fields and submits the form. Upon submission, we will check for the presence of a success notification confirming that the birthday was added correctly. For our second test, we'll navigate to the edit page for an existing birthday, where we will modify the name and birthday. Again, after submission, the script will assert that the expected success notification appears, indicating that the update was successful. This structured approach allows us to automate the testing of critical functionalities and ensure that our application provides a seamless user experience. In summary, updating form actions to handle edits is an integral part of improving your web application. We examined creating a dynamic form, coding server endpoints for create and update functionalities, and implementing feedback notifications to users. Furthermore, we touched on integrating Microsoft Playwright to ensure everything runs smoothly through automated testing. Every improvement you make fortifies your application against user frustration while empowering them to manage their data effortlessly. Remember, an engaging interface isn't just about aesthetics. It's about creating an experience users will appreciate. So keep coding, keep testing, and don't forget to refine your applications. Integration isn't just an afterthought, it's a key to user satisfaction. Enjoy the journey of continuous improvement and it's now time to update our birthday data items to include an ID field. This addition will enhance our ability to uniquely identify each birthday entry, making it easier to manage, retrieve, and edit our records effectively. In today's lesson, we will dive into how to evolve our repository to accommodate ID lookups, ensuring our application is as functional as possible. So far, we learned the significance of enhancing form actions in web applications to facilitate easy updates of user data. We discussed how to set up forms that conditionally handle new entries or edits, implement server-side functionality for proper request handling, and provide user feedback upon successful updates. Additionally, we explored using Playwright for automated testing to ensure that our application behaves correctly during user interactions. These steps collectively improve user experience and application reliability. Now, we will talk about incorporating an ID field into our birthday data items and see how this change can streamline our data operations. Next, we will implement a class called birthDentry to represent each birthday record in our application. This class will encapsulate 3 key attributes: ID, name, and birthday. When we create an instance of birthDentry, we will provide it with a unique identifier, along with the name and birthday of the individual. This structure allows us to systematically organize our birthday data while ensuring each entry can be distinctly identified by its ID, which is crucial for efficient data management. Now let's see how we can leverage this structure in our overall application by incorporating a manager class. This will facilitate operations like adding, updating, and retrieving birthday entries with their corresponding IDs. By setting up the birthday manager, we can ensure that our entries are not only stored effectively, but also enhanced with functionalities such as automatic ID generation and CRUD operations. This structured approach simplifies our data handling and empowers us to maintain a clean and organized codebase, ultimately improving the user experience in our application. Now let's see how we can implement the Birthday Manager class, which will serve as the backbone for managing our birthday entries. In this class, we initialize 2 key attributes: entries, an empty list for storing our birthday entries, and currented, which we set to 1 as our starting point for unique IDs. This will help ensure that each entry we create receives a distinct identifier. Next, we will write the addEntry method. This method allows us to add a new birthday entry to the list. When invoked with a name and birthday, it creates a new instance of birthday entry, assigning it the current value of currented, the provided name, and birthday. After appending this new entry to the entries list, we increment the currented by 1 to ensure that future entries will have unique IDs. This systematic approach simplifies tracking and managing birthday entries within our application. Each new entry added is properly structured with a unique ID, thus enhancing the overall functionality and efficiency of our birthday management system. Now let's see how we can implement a method to retrieve an entry by its unique ID in our Birthday Manager class. The getEntryById method serves the essential role of searching through the list of birthday entries stored in the entries attribute. It does this by iterating over each entry in the list and checking whether the ID of the current entry matches the provided entryid. When a match is found, the method immediately returns that specific entry, which enables us to efficiently access detailed information about the birthday entry we are interested in. If no matching entry is found after looping through the entire list, the method returns none. This functionality is crucial since it allows us to either display an entry on the front end or prepare it for further updates or deletions later on. With this method in place, the backend can handle various operations seamlessly, simplifying how we manage the birthday data and ensuring that each entry can be uniquely identified during any subsequent actions. Now let's implement the updateEntry method in our Birthday Manager class, which will allow us to modify existing birthday records using their unique ID. This method starts by attempting to retrieve the birthday entry associated with the provided ID by calling the earlier defined getEntryById method. If a matching entry is found, it proceeds to update both the name and birthday attributes with the new values provided as arguments. This streamlined approach ensures that any modifications are applied directly to the correct entry, reinforcing our data integrity. If the specified ID does not correspond to an existing entry, the method gracefully returns none instead of causing an error, thus maintaining stability in the application. By implementing this functionality, we significantly enhance our ability to manage birthday records effectively, allowing users to keep their information current and accurate. This seamless update process is crucial in fostering a responsive user experience within our application, ensuring that users can easily make changes as needed without hassle. Now that we have established our add and update functionalities, let's incorporate the ability to delete an entry as well. We will implement a method called deleteEntry in our Birthday Manager class, which facilitates the removal of an entry based on its unique ID. This method will utilize the enumerate function to loop through the entries list, providing both the index and the entry itself. By comparing each entry's ID with the provided entryid, we can efficiently identify which entry to delete. If a matching entry is found, we use its index to remove it from the list, ensuring that our data remains clean and accurate. Returning true upon successful deletion helps verify that the action was completed as intended, while returning false signifies that no entry was found with the given ID. This structured approach not only maintains the integrity of our data management, but also allows for straightforward operations when handling user requests in our application. With this feature, users can now remove specific birthday entries seamlessly, enhancing the overall functionality of the Birthday Manager class. Now let's see how we can implement the server endpoints to manage our birthday entries using Flask. We begin by defining 3 key endpoints: one for adding a new birthday entry, one for updating an existing entry, and one for deleting an entry based on its unique ID. First, the add endpoint responds to post requests at /API/birthdays. This function retrieves the JSON data sent in the request, which contains the name and birthday. Then it utilizes the Birthday Manager to add the new entry and returns the newly created entry's details, including its ID. Next, we implement the update endpoint, which handles PUT requests directed at /API/birthdays/int entry ID. Here, we extract the entry ID from the URL and the updated information from the request body. The Birthday Manager updates the specified entry and returns the updated details or a message if the entry is not found. Lastly, the delete endpoint manages delete requests at the same URL pattern, removing an entry by its ID. If the entry is successfully deleted, we send back a confirmation message. Otherwise, we indicate that the entry is not found. This setup allows us to efficiently manage CRUD operations in our application using ID-based actions. Now let's implement our automated testing functionality using Playwright to ensure our API correctly handles adding and updating birthday entries. We begin by importing the necessary Playwright module and defining a run function, where we'll orchestrate our tests. First, we launch a Chromium browser instance and establish a new context. This context is a crucial step as it simulates a fresh user session for each test run. Next, we create a new page within this context to interact with our API. In this page, our first test simulates adding a birthday by sending a post request to the /API/birthdays endpoint with the name John Doe and a specified birthday. Once we receive the response, we assert that the name returned matches what we sent, validating the add functionality. Following the addition, we extract the ID of the newly created entry and use it to test the update functionality. A PUT request is sent to the corresponding endpoint to update the birthday entry to John Smith. Again, we check the response to ensure the update was successful. Finally, we close the context and the browser, marking the end of our test scenario. This comprehensive setup verifies that our API functions well under the expected conditions and user interactions. To sum up, evolving our repository to allow ID lookups is essential for any data management application. By incorporating an ID field into our birthday entries, we can streamline operations such as retrieving, updating, and deleting records. We've walked through enhancing our data structure, implementing CRUD operations, and ensuring our endpoints handle these enhancements effectively. Lastly, we introduced automated testing, using Playwright to verify our application's operability. As we move forward, keep in mind the fundamental principle of maintaining clean, functional, and efficient code. With these skills under your belt, you're well on your way to mastering data handling in your applications. So keep experimenting, keep learning, and as always, have you ever felt frustrated when working with your test suites? They can easily become messy and overgrown unless you're actively tending to them. Today, we will explore how to keep your test suites tidy, using effective strategies and best practices to ensure your code remains clean, manageable, and easy to maintain. So far, we have learned about the importance of incorporating an ID field into our birthday data model to enhance data management capabilities. We explored how to create a simple class for birthday entries and a manager class to handle create, read, update, and delete CRUD operations effectively. Additionally, we discussed how to set up a Flask API to facilitate these operations and the significance of automated testing with Playwright to ensure functionality. This foundational knowledge equips us to better manage and manipulate our application data. Now, we will cover strategies for tidying up test suites, focusing on 3 essential methods: page object models, extracting action helpers, and designing factory methods. Now let's take a look at how we can implement the page object model for our birthday management feature. We begin by creating a class named BirthdayListPage that serves as a blueprint for interactions with the birthday entry page. In the constructor method, we initialize the class with the page object, which represents the current browser page in Playwright. Next, we define the goTo method, which is responsible for navigating to the birthday page when called. This promotes reuse throughout our testing suite, as we can invoke goTo to access the page without repeating the navigation code in every test. Moving on, we implement the fillName and fillDateOfBirth methods, which are designed to fill in the respective input fields for the birthday entry with the provided parameters. This abstraction allows us to centralize our element locators, enhancing code readability. Finally, the ClickSave method simulates the action of clicking the Save button to submit the birthday entry. By organizing our interactions in this manner, we not only enhance the clarity and maintainability of the test code, but also simplify modifications, as changes only need to occur within the BirthdayListPage class and not in the individual test cases. Now let's take a look at how we can incorporate the BirthdayListPage into our test cases for adding a birthday. This code begins by importing necessary libraries, including Vitest and Playwright from Playwright, along with the BirthdayListPage class that we previously defined. The test_add_birthday function serves as our test case where the actual testing steps will be executed. Next, within this function, we initiate a Playwright session. We launch a Chromium browser instance and create a new page to navigate to our birthday list URL. With our BirthdayListPage instantiated, we can now use the methods defined in that class to interact with the page elements more efficiently. We then utilize the fillName method to enter name, followed by the fillDateOfBirth method to input the date of birth. Finally, we call the ClickSave method to simulate saving the birthday entry. This structured approach not only keeps our test suite clean and organized, but it also ensures that future changes to UI elements can be managed easily within the BirthdayListPage class without cluttering our test files. Now, let's implement the Action Helper function to streamline our test for adding birthdays. This function, add_birthday, will combine common actions into a single reusable definition. It accepts a page object along with name and dob parameters, which represent the name and date of birth we want to input. As we explore the body of this function, you'll notice how it utilizes the Playwright API to automate interactions with the web page. The function begins by filling the name input field with the specified name, followed by populating the date of birth field with the dob parameter. Finally, it simulates a click on the Save button, effectively executing the action of adding a birthday within the application. Next, we will shorten our test code by incorporating this action helper. Instead of repeating the same input routines in each test, we simply call add birthday with the appropriate parameters. This results in cleaner, more readable tests, allowing us to focus on the test objectives rather than the minutiae of the UI interactions. Overall, this approach promotes maintainability and clarity in our test suite. Now let's implement a factory method for creating birthday data objects. This function encapsulates the logic for generating a birthday entry, which helps streamline the setup phase of our tests. By defining a function named createBirthday, we can easily create a dictionary containing the name and date of birth of a birthday entry. This prevents repetitive code throughout our test suite, ensuring that any test requiring a birthday entry can generate one consistently. Next, we'll utilize this factory method within a test case designed to add a birthday. By calling createBirthday, we pass in the name and date of birth, which provides a clean and clear way to construct our test data. This approach increases the maintainability of the tests since, should we need to change the structure of our birthday data, we can simply update the factory method without having to alter every test that constructs a birthday entry. Overall, using factory methods not only makes our tests shorter and more readable, but also guarantees that all tests produce birthday entries that adhere to a standardized format, reinforcing better practices in our test suite management. To wrap things up, keeping your test suites tidy is essential for long-term project success. By implementing page object models, extracting action helpers, and designing factory methods, you make your test code cleaner, more manageable, and easier to understand. As you adopt these strategies, you'll shout Eureka when you see how much easier it becomes to work with your test suites. Remember, neat and tidy test suites will not only save you time, but will also make you look like a testing rock star. So get out there, maintain those test suites, and revel in your new. Now let's take a look at the createBirthday factory method, which serves as a straightforward way to generate birthday entries for our tests. This method accepts 3 parameters: name, DOB, date of birth, and an optional email. Within the method, we start by creating a dictionary called birthday entry, which initially contains the required fields for the birthday entry. If an email address is provided, it is conditionally added to the dictionary, allowing for varied birthday entries based on test needs. This design promotes flexibility and reusability, enabling us to generate different sets of birthday information without duplicating code across our test cases. By using this factory method, we can ensure that we maintain clean and consistent test data. When we run our tests, calling this method provides a clear and concise way to set up required data, reducing clutter and improving readability. Overall, this practice aids in maintaining tidy test suites and simplifies the process of testing variations in data creation. Now let's see how we can implement our test for adding a birthday using the createBirthday factory method. The test, named test_add_birthday, begins by calling the factory method to generate the birthday data for a specific individual, John Doe, with his date of birth and email. This abstraction ensures that the data generation is handled separately from the testing logic, highlighting the benefit of clean and organized code. Next, the test proceeds to interact with the application by passing the created birthday data to the addBirthdayToApp function. This is where our data meets the application logic, simulating the process of adding a birthday entry in the system. Finally, we include an assertion to validate that the result returned from the application confirms the addition of the birthday entry with the message, "Birthday successfully added." This structure showcases the effectiveness of using factory methods in tests, improving code clarity and reusability while allowing for easy updates to the data generation process as requirements change. Now let's implement a refined version of our createBirthday method by introducing default parameter values. This enhancement will allow us to initialize birthday entries without specifying every detail each time, leading to more streamlined code execution. In the updated method, we set default values for the parameters. Name is given a default of default name, and DOBI defaults to 200101. The email parameter remains optional, set to none if not provided. This means that callers can simply invoke create birthday without arguments, and they will receive a complete birthday entry with the defaults in place. Furthermore, we use a dictionary to encapsulate the birthday data, ensuring easy access to the attributes through dictionary keys. If an email is provided, it is conditionally added to the birthday entry. This design not only simplifies the process of creating common birthday data for our tests, as seen in the subsequent test default birthday function, but it also promotes clarity by explicitly checking for parameter values. The test then asserts that the defaults are correctly set, ensuring our factory method functions as intended while minimizing code duplication and maintaining an organized test suite. Now let's take a look at how we can implement the Create Birthday factory method, which simplifies the creation of birthday entries for our tests. This method starts by accepting 3 parameters: name, DOB, date of birth, and an optional email. By providing default values for name and DOB, we allow for easy and quick generation of basic birthday entries without requiring the caller to specify every argument. This flexibility can save time in test setups where certain values are reused frequently. Within the function, we create a dictionary named birthday that holds the name and DOB, ensuring that these values are easily accessible as structured data. If an email is provided, it is added to the dictionary, giving us the ability to enrich the birthday entry with additional information if needed. This design not only promotes readability, but also enhances maintainability, as any changes to the entry structure can be managed in one place. By encapsulating the logic of birthday entry creation within this factory method, we streamline our testing process, making it clearer what data we are working with and reducing redundancy in our test code. Now let's implement the following Playwright test that demonstrates how to seamlessly integrate the Create Birthday factory method into our test setup. This code begins by launching a Chromium browser instance using Playwright's Async Context Manager, ensuring that resources are properly managed during the test. Once the browser is active, we navigate to the specified web page dedicated to birthday entries. The next crucial step is creating the birthday data by calling our Create Birthday method with relevant parameters, such as the name, date of birth, and email. This factory method generates a structured dictionary containing the birthday details, which we will use in subsequent interactions. Following this, we use the specific identifiers of the form fields to fill in the birthday entry using the data generated. If an email is provided, we ensure that the email field is populated accordingly. After completing the form, we simulate a click on the Submit button, which triggers the action to add the birthday to the application. Finally, we assert that the expected success message is displayed, confirming that the entry was added successfully, and close the browser to conclude the test. This workflow not only promotes organization, but also simplifies data management during UI testing. As we reflect on our exploration of factory methods today, it's clear they provide a significant advantage in managing test data creation within your Playwright tests. Centralizing object creation not only reduces duplication, but also promotes clarity and maintainability of your code. To summarize, we've discussed the purpose and implementation of factory methods, explored the benefits of maintaining clean test data creation, and highlighted the importance of documentation. We've also illustrated how these methods integrate smoothly into your Playwright test structure, enhancing overall code organization. So, as you continue to develop your test suites with Microsoft Playwright, consider integrating factory methods into your arsenal. Embrace the tidiness and consistency they bring, and enjoy the benefits of a robust testing strategy. Factory methods are more than just a coding technique. They're a way to empower your test suites, paving the way for easier collaboration and continued growth in your testing capabilities. Thank you for joining me in this discussion on factory methods. Happy testing, and keep coding. Now let's implement the to-be-unprocessable entity custom matcher, which will help us assert that a response has a specific status code of 422 and that its body matches an expected output. This function begins by checking whether the status code of the received response is equal to 422. If it's not, we return a structured response indicating a failure, complete with a message that clearly states the discrepancy. This is crucial for debugging, as it directly informs us of the actual status code received. Next, we verify the body of the response against the expected data using an equals function. This function will help us conduct a deep comparison, ensuring that even nested properties match as expected. If there's no match, we again return a failure response, including a specific message indicating that the response bodies did not align. If both checks pass, we conclude by returning a success indicator, affirming that the response adheres to our expected conditions. This matcher encapsulates complex assertions in a single reusable function, enhancing the clarity and maintainability of our tests. Now that we have our custom matcher defined, it's critical to validate its functionality through a comprehensive test suite. Next, we will write the test suite that utilizes the Vitest framework to ensure our matcher behaves as expected. We begin by organizing our tests in a describe block, which clearly defines the scope of our matcher to be unprocessable entity. Within this block, the beforeall hook allows us to extend the expect function with our custom matcher, setting the stage for our assertions. Moving into the actual tests, the first one checks whether an error is appropriately thrown when an invalid response status is provided, specifically when it's anything other than 422. This is important, as we want to ensure our matcher correctly detects unexpected status codes. The second test confirms that no error is thrown when the response successfully returns the status code 422. By using these tests, we gain confidence in the reliability of our matcher, catching potential issues early before they can affect broader test results. This systematic approach to testing not only reinforces our matcher's validity, but also underscores the importance of clear and concise assertions in maintaining robust test suite. Now, let's implement the failure message enhancement for our custom matcher to be unprocessable entity. Within the matcher function, we first check if the received response's data matches the expected values. If they are not equal, we return a structure indicating failure. Importantly, the failure message is designed to provide a detailed output. It utilizes the utils diff function, which visually highlights the differences between the received and expected data structures. This enhancement allows developers to quickly identify discrepancies without having to manually sift through data, thus streamlining the debugging process significantly. By incorporating this detailed comparison into the failure message, we not only make it clear what went wrong when the test fails, but also empower developers to resolve issues more efficiently. This is particularly useful in complex testing scenarios where understanding the nuances of data can be critical. Such an approach ensures that your tests are not only rigorous, but also informative, presenting clear, actionable insights during failure cases that can be invaluable in the debugging phase. Now let's see how we can implement the negation logic in our custom matcher to be unprocessable entity. At the start of the matcher, we introduce a variable called isNot, which refers to the property this is not, determining if the matcher is being used in a negation context. If this is the case, and the received response status is 422, the matcher should return a failure structure. This structure indicates that a non-422 status code was expected, but a 422 was encountered, providing a clear error message for debugging purposes. This approach allows our matcher to adapt flexibly to various testing scenarios. By encapsulating the negation logic right at the beginning, we ensure that any conditions checking for the absence of an unprocessable entity are handled correctly. Following this, the matcher can continue to perform additional checks, such as verifying the body content of the response, allowing for a comprehensive evaluation. This structure enhances the overall functionality of our matcher, ensuring it remains robust and intuitive to use in tests, thereby making our testing process more effective and organized. Now let's take a look at how we can apply our custom matcher in a practical test scenario. In this example, we want to validate the response returned from a function that simulates a form submission. The function, performFormAction, is called with a user created by the createBirthday factory method, where we are intentionally passing invalid data, an unknown date of birth. This is where our to be unprocessable entity, matcha, comes into play, allowing us to make a single assertion that checks both the status code and the content of the response in a concise and readable manner. Instead of having multiple assertions scattered throughout the codebase to validate the response, we encapsulate this logic into one clear line. The expectation here is that the result should yield a 422 status code, along with a JSON object containing an appropriate error message. By utilizing the custom matcher, we enhance the clarity and maintainability of our tests, ensuring our testing code remains organized and easily navigable. This practice ultimately aligns with our goal of maintaining a clean test suite, especially as the complexity of the tests increases over time. In conclusion, creating custom matches is a game changer for enhancing the efficiency and clarity of your testing code. They allow you to encapsulate complex assertion logic into easily reusable and readable functions, significantly reducing code duplication. With custom matches, we can provide detailed error messages that simplify debugging, adapt our logic for negation scenarios, and ultimately streamline our test suites to ensure they remain maintainable as our project scales. By embracing the power of custom matches, you can elevate your testing strategy to a whole new level, ensuring not just that your code works, but that it is also a pleasure to test. Happy coding, and as always, keep your tests clean. Next, we will implement the custom matcher, to be unprocessable entity, which incorporates negation logic to enhance our testing capabilities. The matcher starts by checking if it has been negated using this is not. If the matcher is in a negated state and the received response has a status code of 422, it triggers a failure, returning a message that clearly indicates the expectation was not met. This failure message is vital for debugging, as it provides clear feedback on the test result. The matcher then proceeds to check for the expected status code. If the received response does not have a status of 422, it returns another failure message, which informs the user exactly what the received status was, thus maintaining clarity throughout. The matcher doesn't stop here. It also validates the response body against any expected data. If there is a mismatch, it returns a failure with a specific message that includes a diff output to highlight the differences. If all checks pass, the matcher confirms success, allowing us to encapsulate complex validation logic concisely and reusably in our tests. Now let's see how we can put our custom matcher to be unprocessable entity to the test using Vitest. In this test suite, we start by extending the expect API with our custom matcher within a beforall hook, ensuring it's available for all subsequent tests. Next, we implement a series of assertions to thoroughly validate the matcher's behavior. The first test checks that an exception is thrown if the status of the response is anything other than 422. This ensures that our matcher correctly identifies non-unprocessable responses. Moving on, the second test confirms that the matcher passes smoothly when the status is exactly 422, highlighting its basic functionality. We then address the critical aspect of negation logic with the third test. Here, we assert that if the status is 422, the negation should cause the test to fail, as it contradicts our expectation for a response not to be unprocessable. Finally, we ensure our matcher behaves as intended under negation in the last test, validating that it passes without issue when the status is anything other than 422. This structured approach solidifies our matcher's robustness and prepares us for diverse testing scenarios. Now let's implement a matcher called To Be Invalid Submission, which focuses on ensuring form submissions behave as expected in the context of user input validation. This matcher uses negation logic to clearly define what constitutes an invalid submission. First, we check if the matcher is being negated by evaluating the this is not property. If this property is true but the received submission is valid, we return a failure condition. In this case, we provide a clear error message indicating that we expected an invalid submission but received a valid one. This immediate feedback helps clarify what went wrong in our tests. Next, if the submission is invalid, the matcher passes, reinforcing the logic we are asserting. If the submission is valid and the matcher is not negated, we return a failure response, again with a descriptive message. This way of implementing negation aspects not only enhances the matcher's utility, but also improves our ability to articulate complex scenarios. By constructing our matcher in this manner, we ensure that error conditions are communicated effectively, making it easier for developers to understand the outcomes during testing. Creating custom matches with negation capabilities ultimately redefines how we approach testing. The clarity and precision we gain from this practice not only saves time, but also reduces stress when navigating complex code. With flexible matches handling various logical conditions, we succeed in writing more expressive, human-readable tests. This mastery over custom matches allows us to focus on higher-level application logics, rather than getting tangled in verbose assertions scattered across our test suite. We craft elegant, concise test cases that describe behavior rather than implementation, maintaining engagement and maintaining excitement as we evolve our testing practices. As we've explored today, the implementation of custom matcher logic with effective negation opens a world of possibilities for our testing. By ensuring we cover various scenarios, including positive results and nuanced negatives, we make our tests robust. By combining well-crafted messages with clean logic, we enhance not only the maintainability and readability of our code, but also preserve the joy of coding itself. Custom matches elevate the overall testing framework, streamlining practices into manageable, good-looking assertions that tell a full story of behavior without clutter. This is what modern testing should embody: a seamless blend of clarity and power, all within the structures that our frameworks provide. This wraps up our exploration of implementing custom matcher logic with negation capabilities. Remember, each matcher you create is a tool, one that should offer clarity as much as enforcing correctness in our assertions. Keep honing those skills and now let's see how we can implement a modular authentication function that is separate from our web framework logic. First, we create an auth.py module that contains the Authenticate function. This function takes a username and password as parameters and checks them against a predefined user star, which holds valid credentials. If the username and password match an entry in this star, the function returns true, indicating a successful authentication. If they do not match, it returns false, providing a clear way to manage user validation without being tied to the complexities of the framework. Next, in our main application file, app.py, we import this Authenticate function to streamline the login process. Here, we handle incoming post requests at the login route. When a request is received, we pause the JSON payload to extract the username and password. If both are present, we call the standalone Authenticate function to verify the credentials. This separation not only enhances maintainability, but also simplifies the process of testing our authentication logic independently from the web framework, ensuring that our code remains clean and focused. Now let's see how we can implement our authentication logic in a dedicated module called auth.py. This module contains the Authenticate function, which takes in a username and password. Inside, we define a simple user star, a dictionary that maps usernames to their corresponding passwords. The function checks if the provided username exists in the user star and validates whether the supplied password matches the starred password. If both conditions are met, the function returns true, indicating a successful authentication. Otherwise, it returns false. This design promotes better organization of our code and ensures that the authentication logic can be tested independently from the web framework. Next, we will write our Flask application in a file named app.py, where we will integrate the authentication logic within our login route. We import the Authenticate function from auth. The login route listens for post requests and retrieves the JSON data sent to it, specifically looking for username and password. When the user submits their credentials, the route invokes the Authenticate function, passing the extracted username and password. If authentication is successful, a success message is returned. Otherwise, a 401 unauthorized error is triggered. This separation allows us to maintain a clean architecture while effectively handling user authentication. Now let's see how we can implement our test cases for the Authenticate function using the Vitest framework. In our testing file, we begin by importing the necessary modules, including Vitest and the Authenticate function from our Authentication module. This setup allows us to isolate our tests from the web framework and focus solely on the business logic of authentication. Next, we define our test functions. The test authenticate success function checks that valid user credentials return a successful authentication result, asserting that the function returns true when both correct username and password are provided for existing users. This ensures that our authentication logic works as intended for expected input. Following this, we implement the test authenticate failure function, which focuses on testing invalid scenarios. Here, we assert that when an incorrect password is used or a non-existent username is given, the function returns false. This is crucial for validating our logic against possible failure cases and ensures that users cannot authenticate with wrong credentials. By organizing our tests this way, we ensure that our authentication function is both reliable and easy to maintain, promoting better practices in our code development. Next, we will implement a command line interface, CLI, that utilizes our previously defined authentication logic. In this example, we create a new script named CLI, where we first import the authenticate function from our auth, module. This allows us to leverage the logic we encapsulated earlier for user authentication without any need for alterations. Now, let's take a look at how the main function operates. Within this function, we prompt the user to enter their username and password. These inputs are captured through the input function, which presents a simple interface for users. After obtaining these credentials, we call the authenticate function with the provided username and password as arguments. If the authentication is successful, the program informs the user with a success message. Otherwise, it indicates a failed login attempt. Finally, we ensure that the main function runs only when the script is executed directly, following the typical Python convention. This CLI script exemplifies how we can repurpose our authentication logic across different contexts, emphasizing the importance of modularity in code design for better reusability and maintainability. Now let's implement input validation in our authentication function to ensure it handles incorrect types gracefully. In this updated version of the authenticate function, we start by checking if both the username and password are strings. If either is not a string, we raise a value error with a clear message indicating that the inputs must be strings. This preemptive validation enhances the robustness of our function, allowing us to catch type errors early and avoid potential issues during execution. Next, we retain a simple user star, which holds valid username-password pairs for verification. The function checks whether the provided username exists in this star and whether the corresponding password matches the starred password. If both conditions are satisfied, the function returns true, indicating a successful authentication. If not, it defaults to returning false. By including this validation in our logic, we create a self-contained authentication function that not only performs its primary task, but also ensures that the inputs are valid before any authentication checks are made. This practice reduces reliance on the web framework's input handling and keeps our domain logic clean and maintainable. In conclusion, extracting logic from frameworks not only enhances the testability of our code, it also provides greater flexibility and reusability. We can ensure that our core business logic remains isolated and clean, allowing for easier updates and adaptations later on. So far, we have used various examples to demonstrate how extracting domain logic improves our applications. We've talked about creating a modular authentication function, writing test cases for it, and even reusing this logic across multiple contexts. The technique we've explored is not limited to authentication. It can be applied across a wide range of functionalities in software development. As best practices evolve, adopting an architecture that fosters separation of concerns and domain logic extraction will surely benefit anyone looking to improve code quality and maintainability in their apps. Now let's take a look at how we can streamline the form processing by extracting the validation logic into a separate function. The initial function, processForm, retrieves the user's birthday from the incoming request and attempts to validate it using the isValidBirthday function. Initially, the function gathers the form data by reading the request text and parses it into key-value pairs. It specifically looks for the birthday input. If the validation fails, meaning the format of the birthday does not meet our criteria, it returns a 400 status response along with an informative error message. This encapsulates the basic validation logic, but tightly coupling it with the form processing hinders reusability. Next, we'll refactor by migrating the validation logic into a new birthday repository module. This modular approach allows us to centralize the validation logic, thereby enhancing maintainability. Once we import the isValidBirthday function from the repository, our form action now succinctly checks for a valid birthday, fostering cleaner code. This transition illustrates how separating concerns can vastly improve code structures and facilitate easier testing and future enhancement. Now let's take a look at how we can create the isValidBirthday function, which serves as the cornerstone of our birthday validation logic. This function is designed to ensure that any input date adheres to the standardized format of YYYYMMDD. We achieve this by employing regular expressions, which allow for a concise and efficient check against our predefined date pattern. In this implementation, the function first imports the necessary array module for regex operations. It then defines a pattern that matches the exact structure of a valid date format, specifically looking for 4 digits representing the year, followed by 2 digits for the month and 2 for the day, all separated by hyphens. Once the pattern is established, the function employs arrayMatch to check if the provided birthday matches this format. The use of isNotNone in the return statement not only conveys whether the validation passed, but also enables straightforward integration into other parts of the application. This encapsulation allows for seamless migration of the validation logic out of our form action, maintaining a clean interface for further development and testing. By structuring our module this way, we enhance reusability while keeping our validation logic neatly organized. Next, we will modify our form action to integrate the isValidBirthday function we created in the previous steps. This change enhances our form logic by separating the validation duties from the form processing itself, promoting cleaner, more modular code. In the updated form action, we first import the isValidBirthday function from our birthday repository. This allows us to leverage our newly established validation logic. Now, let's see how we can implement this in our form action. We begin by reading the incoming request data and extracting the birthday input using the URL search params method. Once we have the birthday, we validate it by calling isValidBirthday. If the birthday doesn't meet the expected format, we promptly return an error response with a status code of 400, indicating a bad request. This clear separation of concerns ensures that our validation logic can be reused throughout the application without repetition. By employing this modular approach, we not only streamline our form logic, but also enhance the maintainability of our code. This method allows for cleaner testing and potential future enhancements, such as adding additional validation rules or related functionality, without complicating the form processing flow. Now let's implement the testing for our isValidBirthday function to ensure our validation logic functions as intended. We begin by importing the Vitest framework and the isValidBirthday function from our birthday repository module. This allows us to access our validation logic directly in the test environment. Next, we define 2 test functions. The first, testValidBirthdays, is designed to verify that correctly formatted inputs return true. We check 2 valid birthday strings, 1990.101 and 2012.31, with assertions confirming that these calls return expected positive results. This reinforces our confidence in the correctness of the implementation. Then we have test invalid birthdays, which checks various incorrect formats to ensure our function catches errors. We include tests for formats such as 1011990, which uses the wrong format, and 1990.101, which employs a wrong separator. Additional cases check for invalid month and day values, affirming that our validation function is not only strict, but also robust against typical errors users might make. Running these tests will help us catch any issues, ensuring the reliability of our validation logic as we continue improving our application. Now let's see how we can implement our tests for the birthday validation logic we just migrated. We will use the Vitest framework, which is well suited for this purpose due to its simplicity and powerful functionalities. First, we'll create a test file that imports the isValidBirthday function from our birthday repository. In this test file, we'll design a set of test cases to ensure our validation logic behaves as expected. We start with a function named testValidBirthdays. This function will assert that correctly formatted birthdays, such as 1990.101 and 2012.31, are recognized as valid inputs. Next, we will create another function called testInvalidBirthdays, which will deliberately check for various invalid input formats. This includes assertions for wrong formats like 1011990 and incorrect month or day values. This distinction ensures a comprehensive test suite that scrutinizes both valid and invalid conditions. By covering these scenarios, we can confidently guarantee that our validation logic works correctly and handles edge cases effectively. Once we have written these tests, running Vitest against our test suite will allow us to validate that the migration did not compromise any functionality. Successful test execution will confirm that our new architecture is both reliable and robust. Now let's see how we can implement the calculateAge function, which serves to derive a user's age from their birthday. This function takes a string input representing the birthday in the YYYYMMDD format. It begins by converting this string into a datatime object, allowing us to work with date-specific methods easily. Once we have the birthday in this format, we obtain the current date using datatime, today. Next, the function calculates the age by subtracting the birth year from the current year. However, we also need to account for whether the birthday has occurred yet in the current year. This is done by checking if today's month and day are before the birthday month and day, respectively. If today is before the birthday, the function will subtract 1 from the year difference to ensure the age reflects the correct number of complete years. This centralized approach allows us to manage related functionalities more effectively within our birthday repository, enhancing the modularity and maintainability of our application for future features like age verification. Throughout this entire migration process, not only have we externalized validation logic and made it reusable, but we've also strengthened our codebase by ensuring that robust tests validate that our logic holds true. This method of migrating logic creates a more maintainable and less entangled architecture, which is essential for long-term application health. To summarize, we started with a tightly coupled validation logic within a form action and transitioned to a modular approach by migrating this logic into a separate repository. We created a clean interface for validation and ensured our changes were sound by implementing unit tests. The result is a codebase that's easier to read, test, and maintain. This lesson emphasizes the importance of maintaining clean architecture in our applications. By focusing on separation and modularity, we create systems that are not only more productive to develop, but also robust enough to evolve with changing requirements. As you continue to build and refine your applications, remember the power of isolation. It's your ticket to a more maintainable and testable. Creating API endpoints in SvelteKit is both streamlined and powerful, revolutionizing how developers build server-side applications. In this engaging session, we will explore the intricacies of building API endpoints using SvelteKit, showcasing examples and best practices along the way. So far, we learned about migrating validation logic from a form action to a separate repository to enhance the maintainability and testability of our application. We implemented a birthday repository for birthday validation and streamlined the form action to utilize this modular approach. Additionally, we stressed the importance of creating unit tests to ensure the functionality of our validation logic. This process emphasizes the value of clean architecture and modularity for robust application development. Now, we will talk about creating API endpoints, focusing on the interaction between the server and client and how to manage data effectively. Now let's implement the get function to retrieve all birthday records through our API. In the server.js file, we start by importing the JSON helper from SvelteKit, which allows us to send JSON responses easily. We also import our birthday repository, which will handle the data operations related to birthdays. The get function is defined as an asynchronous function where we call birthday repository getAll to fetch all birthday entries. This function encapsulates the logic for accessing the birthday records, promoting a clean separation of concerns. Following the data retrieval, we use the JSON function to return the data in a structured format, specifically as a JSON object containing the birthdays. This approach not only adheres to res default practices, but also enhances the readability and usability of our API, making it intuitive for front-end applications to interact with the backend. By structuring the response in this manner, developers can easily handle the data on the client side, enabling smooth communication between the front-end and back-end services. Now let's examine how we can implement a post method to accept birthday information and save it to our repository. In this code, we define an asynchronous function named post, which is structured to handle incoming requests. The request object is destructured to extract the name and date of birth from the parsed JSON body of the request. This is done using the awaitRequest JSON method, which allows us to interact with the data sent by the client effectively. After extracting the necessary information, we call the repository function addNew, passing in an object containing name and dob. This method is responsible for saving the birthday details in the underlying data storage. To provide feedback to the client about the success of their request, we use the JSON helper from SvelteKit. This enables us to return a structured response containing a message indicating that the birthday was successfully added. This practice not only enhances the user experience, but adheres to good API design principles by providing meaningful feedback to the client. Now let's implement the validation logic in our post method to ensure the integrity of the data being processed. The code begins by extracting the name and date of birth from the request's JSON body. Following this, we include an essential check. If either name or dob is missing, the function immediately returns a 400 bad request status, along with a meaningful error message. This approach helps inform the client exactly why the request failed, promoting clearer communication. Next, we attempt to save the birthday data using our repository's addNew method. However, it's crucial to handle potential errors that may arise during this process. If the addition fails, we return a 422 unprocessable entity status alongside the specific error encountered. This two-tier validation process not only reinforces data integrity, but also ensures that our API responds appropriately to various failure modes. Finally, upon successfully adding the birthday, we send back a success message, confirming the action to the client in a structured JSON format. This ensures a smooth interaction between the client and server while maintaining robust error handling. Next, we will implement the put method to update existing birthday records. In our +server.js file, we start by importing necessary modules and defining the put function, which allows us to handle incoming requests. We begin by extracting the id from the URL parameters, which specifies which birthday record we intend to modify. Now, let's take a look at how we retrieve the new data from the request body. We parse the JSON from the request to get the name and dob, ensuring we have the updated values ready for processing. To maintain data integrity, we perform validation checks to confirm that both name and DOB are provided. If not, we throw an error with a 400 bad request status. Once the validations pass, we invoke the update method of our birthday repository, passing in the id and updated details. This method handles the logic for making changes to our data store. If the update operation encounters an issue, we throw a 422 unprocessable entity error. Finally, if everything goes smoothly, we return a success message as a JSON response, confirming that the birthday record has been updated successfully. Now let's implement the delete functionality for our birthday records. We will modify the birthday/id/plus server JS file to handle requests that aim to delete specific entries. The delete function we will define takes a parameter, id, which is extracted from the URL parameters. This id is crucial as it identifies which birthday entry we want to remove. In the logic of the delete method, we call the remove method from our birthday repository. This method attempts to delete the birthday corresponding to the provided id. It's essential to check if there was an error during this operation. If an error occurs, such as trying to delete an entry that doesn't exist, a 400 for not found error will be thrown, signaling the client that the requested resource could not be found. On the other hand, if the deletion is successful, we return a JSON response that includes a success message, indicating that the birthday was deleted successfully. This simple yet effective implementation allows users to manage their birthday records directly through our API, rounding out the CRUD operations in a clean manner. Now let's see how we can implement testing for our SvelteKit API endpoints using Playwright. First, we define a test case for our post endpoint, which is responsible for adding a new birthday. The test sends a post request to the /API/birthdays endpoint with a sample birthday entry, and we use an expect statement to check that the response is successful, indicated by the OK method returning true. This ensures that when we try to add a new birthday, the API correctly acknowledges the request. Next, we will write a test case for the get endpoint, which retrieves all birthdays. In this test, we send a GET request to the same endpoint and gather the return data in JSON format. We then validate that the response contains the birthdays property, confirming that the structure of the response is as expected. Additionally, we check that the length of the birthdays array is greater than 0, ensuring that we actually have data returned. These tests are crucial as they help maintain the reliability of our API, facilitating ongoing development and changes with confidence. As we wrap up our exploration of API endpoint creation using SvelteKit, remember that the goal is not just to create functional endpoints, but to design an API that is robust and well-tested. This approach allows for easier scalability and enhancements down the line. In summary, today we examined SvelteKit API endpoints, demonstrating how to create, retrieve, update, and delete data effectively. We've also touched on validation, error handling, and the importance of testing to ensure a reliable API. Armed with this knowledge, you have the foundational tools to build powerful applications that can serve data seamlessly. Always keep experimenting and enhancing your skills in API design and implementation, as these are crucial for successful web application development. Implementing test-driven development, or TDD, is a highly effective methodology in software engineering that ensures the integrity and functionality of your code while streamlining the development process. TDD centers around a simple but powerful mantra: test first, code second. This approach forces us to think critically about the requirements and expected behavior of our application before we write additional code. Today, we'll unpack how to implement API endpoints using TDD in SvelteKit, reinforcing our understanding of building powerful web applications. So far, we covered the fundamentals of creating API endpoints in SvelteKit, managing data with various HTTP methods, along with validation and error handling techniques. Now we will delve into TDD, exploring how it can enhance our coding practices while interacting with API endpoints. Now let's implement a test case to validate if a person's birthday is in the future. In this function, test birthday in future, we simulate a post request to our birthday API with a future date for the date of birth. The expectation here is clear. Since the birth date is in the future, the API should return a 400 bad request status along with the corresponding error message. This test is crucial. It embodies the TDD principle of starting with a failing test, as the validation logic for future dates has not yet been implemented. Now let's see how a test case checks the response of the API. It asserts that the status code is indeed 400, indicating an error, and further confirms that the returned JSON message matches the expected error. This layered validation of response ensures that we capture the intended functionality before moving on to the implementation phase, highlighting the significance of precise requirements in software development. Such tests not only guide our coding, but also reinforce the reliability of the features being built. Now let's implement the logic required for our birthday validation. We begin by defining a utility function called isBirthdayInFuture, which accepts a date of birth as input. This function utilizes the DataTime module to parse the provided date string and compare it to the current date and time. By checking if the parsed date is greater than the current date, the function determines if the birthday is in the future, returning a Boolean value accordingly. Next, we modify our post endpoint within the addBirthday function to incorporate this validation. After extracting the name and date of birth from the incoming request data, we invoke the isBirthdayInFuture function. If the function returns true, indicating the provided date is in the future, we generate an error response. This response informs the user that birthdays cannot be set in the future, utilizing a standardized error format. If the input date passes the validation, we assume that a separate method, addNew, saves the birthday information to our database, and we respond with a success message. This structured approach not only adheres to best practices, but also exemplifies the test-driven development cycle by ensuring our application behaves as expected after implementing the validation logic. Now let's take a look at the test we wrote to ensure our API correctly handles invalid date formats. This test, named TestInvalidDateFormat, sends a post request to the birthday API with an improperly formatted date, specifically 10/1/2020. The expectation here is that the API will respond with a 400 bad request status code, indicating that something went wrong with the input. Moreover, the response should contain a clear error message stating, invalid date format, use YYYYMMDD. This forms an important part of our validation strategy, ensuring that users cannot submit invalid birthday entries. Next, we will implement the actual logic within the addBirthday function to enforce date format validation. By utilizing a try-except block, we attempt to parse the incoming date using the expected format of YYYYMMDD. If parsing fails, a value error is raised, and we return an appropriate error message and status code. Above this, we also check if the provided birthday is in the future, reusing the logic we previously crafted. Lastly, if all validations pass, we proceed to add the birthday entry, confirming a successful addition of the data while maintaining robust error handling. Next, we'll write a test case to ensure that our API correctly handles scenarios where required fields are missing. Specifically, we want to validate the presence of the name when a user attempts to add a birthday without it. The test is structured to make a post request to the /API/birthdays endpoint with only the date of birth provided. We assert that the response returns a 400 status code and a specific error message stating that the name is required, reinforcing our commitment to robust input validation. Now, let's implement the logic inside our addBirthday function to check for the presence of the name field. After extracting the input data from the request, we perform a validation check to see if the name is empty. If it is, we respond with an appropriate error message and a 400 status code. This early validation prevents further processing if the input is not valid, ensuring our API does not accept incomplete data. This method of validating input highlights the importance of clear and actionable error reporting, making it easier for users to understand what went wrong and how to correct it. With these validations in place, we enhance the reliability of our application's functionality. Next, we will implement our centralized validation function to streamline the birthday data checks. We start by defining a function called validate birthday data, which takes in a data dictionary. This function first checks whether the name key is present. If not, it returns an error response indicating that the name is required. Following that, it retrieves the date of birth and checks its presence as well, ensuring that the user provides this essential information. To enhance our validation, we'll also attempt to pause the date using the correct format, handling potential errors using a try-except block. If the date format is incorrect, the catch will provide feedback to inform the user. Additionally, we utilize the existing utility function, isBirthday to verify that the submitted birthday is not set in the future. If all checks pass, the function returns none, allowing the process to continue. Now let's see how we can utilize this validation function in our addBirthday method. We invoke our validation function with the request data and check for any validation response. If an error is found, we return that error. Otherwise, we proceed to add the new birthday entry. This modular approach not only keeps our addBirthday function clean, but also fosters efficient code maintenance. Next, we will write a test to verify that our API can successfully update a birthday. This test begins by simulating the creation of a new birthday entry using a post request. We provide a JSON object containing the name and date of birth, which sets up the context for our update operation. After successfully adding the entry, we execute a put request targeting the specific birthday entry, identified by its unique ID. In this request, we include an updated JSON object that modifies the name while keeping the date of birth the same. The key assertions in this test validate that the response status code is 200, indicating success. We also check that the returned message confirms the update was successful. This structured approach ensures that both the addition and update functionalities work seamlessly and aligns with our TDD methodology. By defining the expected behavior in our test first, we can confidently implement the corresponding put method in our API, reinforcing the reliability of our application as we expand its capabilities. This process of writing and validating tests improves our code's robustness and functionality. By embracing TDD, we significantly improve the quality of our code and the overall reliability of our API endpoints in SvelteKit. TDD ensures that the application behaves as we expect and consolidates our feature requirements into a suite of tests that we can run effortlessly as our project evolves. Moreover, each test serves as a living document of the API's requirements, simplified by modular validation functions and precise logic implementations. In conclusion, TDD elevates our development practices to create well-structured, maintainable, and reliable applications. As you continue to build and enhance your APIs, leverage TDD to ensure that your code is not only functional, but also robust against future modifications. Embrace the red-green refactor cycle, write comprehensive tests that cover all functionality, and watch as your coding process transforms into a finely tuned machine that delivers consistent and quality results every time. Happy coding as you embark on your journey with. Let's delve into updating our root loader to use the API in a SvelteKit application. In this engaging tutorial, we'll explore the exciting implementation of the get/API/birthdays endpoint using the SvelteKit fetch function. We've previously grasped the principles of test-driven development, allowing us to create robust API endpoints effectively. Now, we will enhance our application by integrating this functionality into our loaders, while ensuring we are adhering to TDD principles throughout the process. So far, we learned about the principles of test-driven development, TDD in software engineering, focusing on the red-green refactor cycle, which involves writing failing tests, implementing code to pass those tests, and refining the code afterwards. We explored how to create API endpoints in SvelteKit by applying TDD practices, including validation for user input and error handling. We then discussed the importance of continual testing as we add features, such as validating birthdays and handling edge cases. Lastly, we emphasized the value of refactoring to maintain code readability and reliability as our application grows. Now, we will cover updating the root loader to utilize the API, enhancing our application's integration with its backend. Now, let's take a look at the code for creating a stub response for our tests. We define a function called fetchResponseOK that takes an optional response parameter. This function returns an object that simulates a successful response from the fetch API. The object has a status property set to OK, indicating that the request was successful. Moreover, it includes a method named JSON, which when called, returns a promise that resolves with the specified response. This setup makes our tests predictable and allows for easy control over what data is returned without making any actual network requests. By using this stub response, we can effectively isolate our tests and focus on validating the behavior of our loaders as they interact with the expected API responses. Now, let's implement this in our testing suite, ensuring our loaders can be tested in a consistent environment, elevating the reliability of our application as we adhere to test-driven development principles throughout our coding process. Now that we have our stub factory in place, let's see how we can integrate it into our testing framework. We start by importing the fetchResponseOK function from our factory, which will provide us with a reliable stub response during testing. This allows our tests to simulate a successful API call without actually making a network request, fostering a controlled environment for validation. Next, we enhance our import statements by including necessary imports from Vitest. Specifically, we add Roman 6, a function that enables us to create mock functions or spies. This inclusion will be essential in our test setup, as it allows us to track calls to the fetch function and ensure it interacts correctly with our API endpoints. By structuring our imports this way, we establish a solid foundation for our tests, enabling us to validate the behavior of our load function effectively. This organization not only aids in readability, but also adheres to best practices in test-driven development. As we progress, we will utilize these imports to create tests that confirm our load function properly fetches data from the defined API, maintaining the integrity of our application as we integrate new features. Next, we will write the test for our birthdays load function, which ensures that our logic correctly interacts with the API. In this test, we begin by defining a block that describes the behavior we are validating. Inside this block, we create a test case which asserts that our load function calls the fetch method with the correct API endpoint, specifically /API/birthdays. To accomplish this, we first set up a mock for the fetch function using Vitest's spy capabilities, allowing us to track its invocations. We then prepare the mock to respond with a controlled output, utilizing a stubbed response that we defined earlier. This setup enables us to simulate a response without actually hitting the network, preserving our testing environment's integrity. Next, we invoke the load function, supplying it with our mocked fetch function. Finally, we include an expectation to verify that fetch was called with the anticipated endpoint. This test is essential not only for validating our current load function, but also for aligning with test-driven development, TDD, principles, as it will guide our implementation in the subsequent steps. Now let's implement the logic in our load function to fetch birthday data from the API using SvelteKit's fetch feature. The function we are defining is asynchronous, allowing us to use the await keyword to handle the fetch operation seamlessly. By taking the fetch parameter as an argument, we ensure that our function can use a mocked version during tests, facilitating effective test-driven development. Within the body of the function, we will call the fetch method to make a request to the /API/birthdays endpoint. This request retrieves birthday information stored on the server. Once we receive the response, the next step is to parse it as JSON, which converts the data into a format we can work with in our application. This return statement thus ensures that the function yields the birthday data parsed into a JavaScript object, which can then be utilized by our components. This structure allows us to both interact with the API efficiently while adhering to TDD principles, providing a robust foundation for our application. With this implementation, when the load function is executed, it will engage with the defined server-side logic without making an actual HTTP request, enhancing performance and maintaining efficient data handling. Now let's implement a crucial test case to ensure that our load function accurately returns the data fetched from our API. We'll initiate by defining a new test where we set up a mock fetch function using Vitest's VIFN. This mock will simulate an API response by returning a collection of birthday objects, specifically Hercules with a birthday of 1990-40202 and Athene born on 1989-0101. Next, we will mock the response with our fetchResponseOK function, which allows us to return this test data when the load function calls fetch. By doing so, we can ensure that our load function operates as expected in a controlled environment without making actual network requests. After awaiting the return of our load function, we'll assert that the result matches our expected structure, confirming that the load function not only calls fetch correctly, but also properly processes and returns the JSON response. This step solidifies our confidence in the load function's ability to integrate seamlessly with the API, adhering to the principles of test-driven development. As we continue, we can clean up our tests by removing any redundant integration. Since we are moving towards solely utilizing the API, we can remove any direct repository calls that remain in our code. Thus, clear out old methods, such as getAll, that were initially used to gather birthday data directly from the repository. When we implement a side-by-side transition, the structure we have built ensures that we keep our test suite passing while we switch between the old and the new implementations. This will enable a smooth transition without breaking existing functionality provided by our tests. Now let's implement the error handling functionality for our fetch responses. To achieve this, we'll create a new factory function named fetchResponseError that will help us simulate error scenarios during testing. This function takes an error message as an argument and returns an object with a status of error. Within this object, we include a method, JSON, which returns a promise that resolves to an object containing the provided error message. This allows us to standardize our error responses for testing purposes, ensuring our tests can reliably simulate and validate error conditions. Next, we'll now utilize this error response in our tests by crafting a case that expects the load function to handle an error. We'll create a test that simulates a situation where the fetch call returns an error response from the server. In this test, we make use of a mocking library to return our newly created error response when the fetch function is called. After that, we assert that the result from the load function matches our expected error structure, verifying that our application handles API errors gracefully and correctly communicates the issue to the front end. This enhancement ensures our application remains robust and user-friendly even when facing unexpected scenarios. The intricate work done in updating the fetch method showcases how vital it is to maintain a clean architecture, especially in handling different response scenarios from an API. The dynamic handling of both successful and error cases not only improves user experience, but also enhances the reliability of our application. To sum up today's lesson, we delved into how to skillfully transition our root loaders to rely on API endpoints using the SvelteKit fetch function. Through various tests, we emphasized the importance of verifying our implementation against both success and error cases, leveraging the principles of TDD throughout our development process. In the next sessions, we will continue to enhance our application by focusing on more advanced features and possibly the implementation of new API endpoints, helping our system stay organized and well-structured. So let's keep those coding standards high and remember that with TDD at our side, every code line typed is a step towards a more robust application. Stay tuned as we explore further enhancements in this lesson, we will be diving into an essential aspect of developing applications with SvelteKit, using a server hook to seed sample data. This technique is pivotal for setting up your application with initial data, enabling efficient testing and development. So far, we learned about the principles of test-driven development, TDD, and how to effectively create API endpoints in SvelteKit. We explored the SvelteKit fetch function for interacting with APIs while maintaining performance and efficiency. Additionally, we designed tests to validate the functionality of our loaders, ensuring accurate data fetching and error handling. Finally, we emphasized the importance of refining our code through continual testing and maintaining a clean architecture as we enhance our application. Now, we will cover how to leverage server hooks to efficiently seed sample data into our application, facilitating smoother development processes and testing scenarios. Now let's implement the following code to seed our sample birthday data. We begin by importing important modules from Node's file system, FS, and path libraries, specifically write file sync, exist sync, and join. This allows us to interact with the local file system and build path strings. Next, we define a function named seedData. This function is crucial as it checks whether the birthday's data file exists. Using join, we create a path pointing to our birthdays JSON file within the data folder. If this file doesn't exist, we prepare an array of sample data, which includes distinctive objects representing individuals and their birth dates, such as Hercules, Athene, and Zeus. After setting up this sample data, we leverage write file sync to create the JSON file and write our sample data into it in a structured format. The seeding function is invoked immediately to ensure that this setup runs as soon as the server starts, providing readily available data for our application. This approach is particularly beneficial during development, allowing us to have essential data on hand for testing our features effectively. Now let's implement the following code in our birthday fetching route. This code sets up the load function, which will read birthday data from the birthdays JSON file we created earlier. We begin by importing read file sync from the FS module to read files and join from the path module to construct the correct file path. In the load function, we define a variable called dbPath that points to our birthdays JSON file, ensuring we use the absolute path based on the current working directory. We then use read file sync to read the content of this JSON file synchronously, specifying UTF-8 as the character encoding to ensure we get a string representation of the file's content. After reading the data, we parse the JSON string into a JavaScript object using JSONParse, which allows us to work with the data in a structured manner. Finally, the parsed data is returned within an object, where it is assigned to the birthdays property. This structured response is what our application component will utilize to display the birthday information dynamically, allowing us to integrate sample data effectively into our application's logic. Now let's implement the testing setup for our birthday API. We start by importing essential modules from the Vitest library, such as describe, it, expect, and befoeach, which will help us structure our tests. Additionally, we import the load function from our server-side route and the necessary file system functions to handle the birthday data. Next, we define the path to our JSON file containing the birthday data, ensuring we can reference it throughout our tests. Within the describe block, we leverage the befoeach hook to create a clean testing environment before each individual test runs. This is crucial as it checks for the existence of the JSON file and deletes it if present, preventing any test interference caused by leftover data. Following this setup, we write our first test case to ensure that the seeding functionality works correctly. We simulate the seeding process by invoking the seedData function and then use the load function to retrieve the birthday data. Finally, we assert that the retrieved data matches our expected sample array, confirming that the seeding process was successful. This setup ensures our application behaves as intended, adhering to the principles of test-driven development. Now let's see how we can implement a robust data seeding mechanism in our application. The seed data function begins by defining the path to our JSON file that will store the birthday data. It then checks whether the file already exists or if it is empty using the existSync and readFileSync methods. This is crucial because it prevents unnecessary overwriting of existing data, thus ensuring data integrity during development. If the file does not exist or if it is empty, the function proceeds to define a sample array of birthday objects, each containing a name and a birth date. This sample data serves as initial content for our application, making it easier to test and develop features related to birthdays. Once the array is prepared, the writeFileSync method is invoked to create the JSON file and populate it with the sample data in a nicely formatted manner. By implementing this logic, our application can elegantly handle scenarios where the data might already be present, enhancing reliability and user experience during the development and testing phases. At this stage, we have created a robust mechanism for seeding sample data into our SvelteKit application using server hooks. This not only aids in efficient development, but also contributes towards building a well-structured application that can handle data effectively. As a recap, we discussed the role of server hooks in SvelteKit, demonstrating how they can be used to automatically seed sample data into our application. We walked through implementing a server hook, integrating the seeding into our application routing logic, and validating this functionality using tests. We also explored edge cases concerning the behavior of our app when existing data is present, reinforcing good development practices. In the upcoming sessions, we will examine more about database interactions, optimizing data retrieval, and handling more complex user scenarios. Keep coding, stay curious, and I look forward to seeing you in Creating an application without component mocks can significantly enhance the quality and reliability of your code. Today, we're going to dive into some advanced development techniques that will improve your application structure and testing process, particularly focusing on using Microsoft Playwright with Python. The goal here is to help you build real functional tests that interact directly with your application, instead of relying on mocks that can sometimes lead to unreliable tests. So far, we've learned about creating applications with SvelteKit, focusing on using server hooks to seed sample data for efficient development and testing. We discussed the principles of test-driven development, TDD, API endpoint creation, and utilizing the SvelteKit fetch function for optimal performance. Additionally, we explored implementing and testing server hooks for automated data setup, ensuring that our application remains robust and flexible. Finally, we addressed best practices for managing existing data and reinforced our testing framework for validation of functionality. Now, we will cover how to effectively approach testing without using component mocks, and why this practice can lead to more realistic testing scenarios. Now let's see how we can implement a test that fetches user data using Playwright in Python. We begin by importing the necessary modules, specifically Sync Playwright, which allows us to run Playwright in a synchronous manner for ease of setup. The test function, testFetchUser, encapsulates our entire testing logic. Inside this function, we launch a Chromium browser instance using Sync Playwright and create a new page to interact with our application. By navigating to the specified URL, we prepare to test the user fetching feature. Next, we simulate a user interaction by clicking the button designated for fetching user data. To validate our test, we need to ensure that the user information is displayed correctly after clicking the button. We achieve this by waiting for a specific HTML element, a div that contains the user information, to appear using waitForSelector. After confirming that the element is present, we retrieve its content and compare it to the expected result using an assertion. Finally, we close the browser, ensuring that all resources are released. This systematic approach not only tests the functionality of the button, but also verifies that the API call and UI rendering work seamlessly together without relying on mock. Now, let's implement a function to seed our test database with necessary user data before running our Playwright tests. The seed test data function is designed to send a post request to an API endpoint specifically created for this purpose. Inside the function, we define a dictionary named postData that holds the username and email of the test user we want to add to our database. By utilizing Python's requests library, we make an HTTP request to the endpoint http://localhost 3000/API/seed, along with the user data in JSON format. Our aim is to ensure this request completes successfully by checking if the response status code equals 200, which indicates that the data has been seeded correctly. Next, we will write a test case named testFetchSeededUser that relies on the seeding mechanism. Before proceeding with any UI interactions using Playwright, the test first calls seedTestData. If the seeding fails, we raise an exception to halt the test execution. Once the data is confirmed to be seeded, we establish the Playwright context to launch a Chromium browser, navigate to our web application, and simulate user actions. This approach ensures our tests run against a consistent and expected state of the application, allowing us to validate the functionality effectively. Now let's dive into the implementation of error handling for our user fetching functionality. First, we define an asynchronous function, fetchUser, that attempts to retrieve user data from the API. It uses a try-catch block to manage potential errors effectively. Within the try block, we initiate a fetch request to the /API/user endpoint and verify if the response is successful by checking the responseOK property. If the response indicates an error, we throw an error to be caught by the catch block. In the catch block, we handle the error gracefully by calling the displayError function, which presents an informative error message to the user in the UI. This approach ensures that our application can respond to unexpected failures, providing feedback seamlessly and ultimately enhancing the user experience. Now let's see how we can implement a Playwright test to validate this error handling mechanism. We simulate a network failure by intercepting the fetch request using Playwright's routing capabilities. By instructing the route to a bot on request, we replicate an error condition. Following this, we trigger the fetch user action in the UI and wait for the error message to be displayed. Finally, we assert that the message shown aligns with what we expect, confirming the application correctly manages error scenarios. Integrating real component tests into your workflow might seem cumbersome at first, as it requires more setup than using mocks. However, the benefits far outweigh the initial overhead. By ensuring that your tests reflect real user interactions and API responses, you create a safety net that can catch potential issues early on. This results in more maintainable code that will ultimately save you time and resources in the long run. So let's sum up where we are now. We've been through avoiding component mocks in our tests and have learned to engage with real components within our application. We discussed how actual API calls provide a more realistic development and testing environment, how to seed test data effectively, and how to implement error handling. Each of these strategies contributes to a more robust testing setup. In conclusion, while mock components might have their place in specific scenarios, leveraging real interactions using Playwright opens up a world of possibilities for higher quality assurance. By focusing on integrating real components into your testing strategy, you empower not only your application, but also yourself as a developer, honing skills that ultimately define the quality of. Now let's see how we can implement basic mocking using the Vitest mock library to isolate our tests. We begin by defining a function called getDataFromAPI, which simulates fetching data from an external API. In real-world scenarios, such functions may fail or return unexpected results, making it crucial to control their behavior during tests. To address this, we set up a test for another function, processData, which relies on getDataFromAPI. Here, we utilize the mockApatch method to replace getDataFromAPI with a mock that returns a predefined output instead of calling the actual function. This ensures our test remains focused solely on process data's logic without external dependencies influencing the result. Next, we assert that the output from process data is as expected, validating that our mocking effectively simulates the required data. This approach allows us to ensure the integrity of the function being tested, emphasizing the importance of isolation in unit testing while safeguarding against external factors, thereby strengthening the reliability of our tests. Now let's see how we can implement the core functions for our data processing task. The function getData from API is designed to fetch data from an external API using a GET request. However, since external calls can be unreliable, we need to isolate our tests from these potential failures. Thus, we have a second function called processData, which calls getData from API and processes the retrieved data to return a formatted string that includes a specific value from the data. Next, we will write a test function named testProcessData to ensure that our processData function works as expected, regardless of the API's actual state. Using the mocker feature of Vitest mock, we replace the original getData from API function with a mock that returns a predetermined response, in this case, a dictionary containing a value of 42. This way, we can assert that processData correctly processes this mock response, ensuring our tests are robust and independent from external factors. By controlling the behavior of our dependencies, we create a more stable testing environment focused on the logic within our application. Next, we will look at how to implement a class structure for data fetching and processing. The DataFetcher class is designed to encapsulate the logic for retrieving data from an API, specifically through its fetch method, which executes a GET request to a specified URL and returns the JSON response. Now let's see how the DataProcessor class operates in conjunction with DataFetcher. This class is initialized with an instance of DataFetcher, allowing it to utilize the fetch method to obtain data when the process method is called. The process method retrieves the data, specifically accessing the value key from the fetched data and formatting it into a readable string. To facilitate testing of this class without making actual API calls, we'll employ mocking. In our test setup for the data processor, we create a magic mock to simulate the data fetcher. By configuring the mock to return predefined data when its fetch method is called, we can ensure that our test checks the logic of data processor without the unpredictability of external API calls. This approach allows for a controlled testing environment, confirming that our data processing functionality operates as intended. Now let's take a look at how we can enhance our tests by verifying the call count of methods within our mocked components. In this code snippet, we use the mocker to create a mock instance of our DataFetcher class, allowing us to control its behavior during the test. We begin by setting up our mock, ensuring that the fetch method returns a specific dictionary when invoked, simulating a successful data retrieval. Next, we create an instance of the data processor, passing in our mock fetcher. Once we invoke the process method on the processor, it operates as if it had made a real API call, returning the mocked data. This setup is crucial not only for validating the output of the process method, but also for ensuring that the interactions between the data processor and data fetcher are executed correctly. To validate these interactions, we employ the assertCalledOnce method on our mock. This assertion checks that the fetch method was called exactly once during the execution of the process method, adding an important layer of confidence to our tests. By focusing on both output and interactions, we create robust tests that guarantee our components are integrated seamlessly while remaining isolated from actual external dependencies. Now, let's implement the following code to utilize Vitest fixtures for mocking in our tests. We begin by defining a fixture called mockFetcher, which is responsible for creating a mock instance of our DataFetcher class. Using the mocker utility provided by the Vitest mock library, we instantiate a magic mock object and configure its fetch method to return a specific output, in this case, a dictionary with the value of 99. This ensures that our mock behaves predictably throughout our tests. Next, we will write a test function named testDataProcessor with fixture, which takes mockFetcher as an argument. Inside this function, we instantiate the data processor, passing in our mockFetcher. When we call the process method on the processor, it retrieves the mocked data instead of making an actual API request. We assert that the result matches the expected output, confirming that the processing logic operates correctly. Lastly, we verify that the fetch method of mockFetcher was called exactly once, ensuring our test checks both the accuracy of the output and the interaction with the mocked method. This structured approach enhances the maintainability and readability of our tests. As you see, adopting component mock libraries in your testing strategies can significantly enhance your ability to validate not just the output of your code, but the interactions between your components as well. These practices allow you to ensure that individual components play well together, mimicking real-world behavior while isolating tests effectively. The overall goal of mocking is to create a predictable and controlled environment where you can isolate and test specific functionalities of your code without the risk of side effects from external systems, ensuring your tests are fast and reliable. In summary, using component mock libraries can dramatically improve your testing approach by streamlining dependencies and refining your assertions. This processing allows you to create tests that focus on logic rather than the unpredictable behavior of external services. By learning how to mock classes and functions effectively, you'll have a powerful toolset to ensure that as your application evolves, your tests continue to serve as an accurate reflection of its behavior. This knowledge not only helps you maintain your application, but also elevates the quality of your code, leading to optimal user experiences and a robust software product worthy of deployment. Embrace component mocking as an important aspect of your testing strategy, and you'll find the reliability and maintainability of your code. To successfully set up a Playwright world object, we must first understand the foundational concepts of what a world object is and how it facilitates shared contextual information between our test scenarios. In the realm of Cucumber JS testing, the world object plays a pivotal role, allowing various scenario steps to access and utilize shared data seamlessly. By drawing parallels between Cucumber JS and Playwright's handling of shared states, we can learn how to effectively implement a world object in our Playwright project. Now let's see how we can implement our world class to effectively manage the testing context in Playwright. The world class begins with an initializer that sets up essential attributes: browser, page, and a dictionary for test data. By initializing these attributes to none or an empty dictionary, we create a clean state for our tests. Next, we can enhance our class with methods that allow us to set the browser and page instances. The setBrowser method assigns the browser instance to the class attribute, while setPage does the same for the page. This design enables us to easily access the current browser and page at any point during our tests. Additionally, the methods for getting and setting test data provide a straightforward way to store relevant information, enhancing the modularity of our tests. Overall, this structured approach helps maintain a clear separation of concerns in our test scripts, ensuring that state management does not become a hindrance as we dive deeper into our testing scenarios. Next, we will write the following implementation of our world class that augments its functionality with Playwright's capabilities. This class initializes with none values for the browser and page attributes, along with a dictionary for test data, allowing for seamless management of test information. The startBrowser method employs the Playwright Sync API to launch a Chromium browser instance in a non-headless mode, meaning you can see the browser in action. It creates a new page within that browser, enabling us to navigate and interact with web content. We also implement a closeBrowser method, which checks if the browser instance exists and safely closes it, ensuring resources are released after tests run. The NavigateTo method allows our test scenarios to direct the opened page to specified URLs, facilitating navigation for various tests. This encapsulated design not only simplifies state management of browser and page instances, but also keeps our test scripts cleaner and more organized, laying a strong foundation for effective testing practices with Playwright. Now let's implement the following test scenarios using our world class in a dedicated file for our Playwright tests. We begin by importing the necessary modules, specifically Vitest and our world class. To ensure efficient resource management, we define a fixture named test_world with a module scope. This fixture instantiates our world object, starts the browser, and yields the world instance for use in our tests. After the test runs, resources are cleaned up by closing the browser, encapsulated by the yield statement. Next, we create a specific test function, test navigate to Google, which utilizes our test_world fixture. In this function, we call the navigate to method, directing it to open Google's homepage. The final assertion ensures that the page title reflects our expectation of Google. This streamlined approach demonstrates the benefit of using a world object. It enhances code readability and maintainability by centralizing context and state management within our tests, allowing us to focus on their logic without repetitive setup code across individual test cases. Now let's see how we can implement user registration using our world object. In this code snippet, we define a test function called testRegisterUser, which simulates the process of a user registering on a website. The first step involves setting shared test data, specifically the username and password, utilizing the setTestData method of our world object. This centralization allows us to easily manage and modify test credentials from a single location, promoting better maintainability. Next, the code proceeds to navigate to the registration page using the navigate to method, directing the browser to the specified URL. This is crucial as it allows us to perform operations on the correct context. Once we have reached the registration form, the code fills in the username and password fields by retrieving the previously stored test data through the getTestData method. This modular approach not only enhances code clarity, but also ensures that our test scenarios are coherent and reliable. Finally, we simulate the action of clicking the register button and verify the outcome by asserting that the registration status message indicates success. This structured way of handling user credentials and interactions showcases the power of our world object in facilitating shared data and operations across multiple test scenarios. Now let's take a look at how we can implement an asynchronous version of the world class to leverage Playwright's async capabilities. This async approach allows for non-blocking interactions, enhancing the responsiveness of our tests. In the async world class, we define an init method that initializes the browser instance, page, and a dictionary for test data. Next, we introduce the start browser method, which utilizes the async with statement alongside Playwright's async Playwright context manager. This method asynchronously launches a Chromium browser instance, ensuring that our web interactions occur in a separate, non-blocking way. As we create a new page, we set it to the self-page attribute for later use. To manage the closure of the browser, we implement the closeBrowser method, which checks if the browser was opened before attempting to close it asynchronously. Additionally, the navigate_to method allows us to navigate to a specified URL, again making use of the await syntax to ensure that our code executes without delay. This structure not only streamlines asynchronous operations, but also maintains clean state management, providing an efficient framework for our testing needs. Having a robust world object allows for cleaner code, better maintainability, and eases the sharing of state and test data among scenarios. The use of fixtures with the world object grants us a way to manage browser instances, pages, and other critical testing components while keeping our test scripts straightforward. We've covered a lot of ground in this lesson, from the basics of setting up a world object to integrating it into our Playwright tests with both synchronous and asynchronous implementations. By implementing a world object, you can streamline your testing process, making it clearer and easier to manage, an essential skill as your testing scenarios grow in complexity. In conclusion, the playbook for setting up a Playwright World object revolves around creating an efficient system for shared data and functionality that serves as the backbone of your test scenarios. With this in mind, you can now confidently explore innovative ways to structure your testing environment, propelling your test efforts to new heights. Thank you for joining me in this journey, and I hope you're excited to apply what you've learned in your upcoming test. Now let's see how we can implement step definitions in our Playwright project using the Vitest BDD library. We begin by importing the necessary components, such as scenarios, given, when, and then, which facilitate the connection between our Gherkin scenarios and the Python functions that execute them. The scenarios function reads the specified feature file, linking it directly to our code logic. Next, we define our first step with the @given decorator, which specifies that when the scenario states, "I am on the home page," the navigate to homepage function will be triggered. Within this function, we use the world object to direct the page to load the homepage URL. Similarly, using the @when decorator, we link the action of clicking the login button to the click login button function, where we programmatically click the corresponding element on the page. Finally, with the @then decorator, we define the expected outcome in the validate login form function, asserting that the login form is visible after the actions preceding it. This structured approach allows us to create clear, maintainable, and executable tests that bridge the gap between human-readable specifications and the automated actions performed by Playwright. Now let's see how we can implement parameterized steps to enhance our test scenarios. Here, we define a step that allows us to input a username and password dynamically. By using the parsers module, we specify the expected variables directly in our Gherkin syntax. When the step is executed, the enter credentials function takes these parameters and fills in the appropriate fields on the web page. This approach promotes the reusability of our step definitions across different scenarios, enabling us to easily test various sets of credentials without having to duplicate code. Next, we'll look at a corresponding Gherkin feature file that complements our step definition. This file outlines a scenario involving a successful login operation that includes navigating to the home page and then entering a specific username and password. When structured in this way, our tests become easier to read and maintain, clearly reflecting the user interactions that we want to validate. This combination of Gherkin for human-readable specifications and Python code for execution provides a robust framework for our testing processes. Now, let's see how we can implement weighting mechanisms within our step definitions to handle dynamic content. The first function, submit login form, is structured to interact with the login interface. When this step is called, it simulates a user clicking the submit button to log in. Following the submission, we have the validate dashboard function, which ensures that we wait for the user dashboard to appear after the login action. This is where the wait for selector method becomes essential. It effectively pauses the execution until the specified selector, representing the dashboard, is visible on the page. The timeout of 5,000 milliseconds indicates that if the element does not appear within this timeframe, the test will fail. This approach is crucial for mitigating timing issues that could arise from network latency or slow loading elements, thereby enhancing the reliability of our test automation. Finally, by asserting the visibility of the dashboard, we confirm that the expected outcome of the login process has been achieved, solidifying the connection between user actions and system responses in our automated testing framework. Now let's implement error handling in our step definitions to improve the robustness of our tests. The code starts with a decorator that specifies the expected Gherkin step, linking it to our implementation. Inside the validate login form function, we use a try-except block to manage potential assertion errors gracefully. Specifically, we check if the login form is visible on the page. If it's not, the assertion will raise an assertion error, which we catch to provide a meaningful error message. This message alerts users to check if the previous actions in the test were executed successfully. By giving clear feedback through printed messages, we enhance the troubleshooting process, making it easier to identify what might have gone wrong. This method not only enables our tests to fail gracefully, but also aids in understanding the flow of test execution. Such error handling ensures that our test automation framework is not only resilient, but also user-friendly, guiding developers in identifying issues during test failures. Now let's see how we can implement a reusable function to streamline our step definitions. The function, Open Browser and Navigate, is designed to encapsulate the task of opening the browser and navigating to a specified URL. By passing the world object and the desired URL as parameters, we can easily direct the browser to any page. Next, we integrate this function into our step definitions using the @given decorator to simplify the behavior required when a scenario indicates that the user should be on the home page. Instead of repeating the navigation logic throughout our tests, we simply call Open Browser and Navigate within the Navigate to Homepage function while providing the homepage URL. This approach adheres to the dry, don't repeat yourself principle, ensuring that our code remains clean and maintainable. Ultimately, this structure allows us to efficiently manage related tasks in one place, making our test codebase more organized. By abstracting common behaviors into dedicated functions, we also enable easier updates and modifications, contributing to a robust and flexible testing framework. Finally, let's consider the importance of using descriptive names for our step definitions. While it might seem trivial, well-named functions improve readability and help anyone looking at the code understand its intent quickly. For instance, instead of a generic name like check form visibility, we can use validate login form to clarify what is being tested. By using specific names, we create a self-documenting codebase, making it easier for both the current and future developers to grasp the logic without diving into the implementation details. As we wrap up our exploration of step definitions, we have gained insights into their crucial role in linking our Gherkin scenarios to Python code. From parameterized steps to error handling and maintaining clean code, we now have a toolkit that empowers us to write robust Playwright-based tests. In summary, implementing step definitions adds immense value to our testing framework, allowing us to maintain organized and efficient end-to-end tests that directly reflect our specifications. By following the principles outlined today, you're well equipped to enhance your test automation efforts and create a more effective testing solution tailored to your application's needs. Thank you for joining this session on step definitions. Now it's time to take this knowledge and start implementing step definitions in your projects, improving your test automation game. Many web applications will involve authenticating users. Authentication is critical to ensure that only authorized individuals can access certain resources or perform specific actions within the application. In this lesson, we'll dive into how to test authentication flows using Playwright, a powerful framework for end-to-end testing. So far, we covered writing feature files and step definitions using Gherkin syntax alongside the Playwright API. Now we will talk about authenticating users in our web applications and how to write tests that validate these authentication mechanisms effectively. Now let's see how we can implement a test for user authentication using Playwright. The first step in our code is to set up a function named test_login, which will encapsulate our login test logic. Within this function, we initiate a Playwright session and launch a Chromium browser instance, allowing us to interact with our web application. Next, we navigate to the login page of the application with the goTo method. This is where we fill in the login form by targeting the username and password input fields using Playwright's fill method. We employ the click method to simulate clicking the submit button, initiating the login process. Immediately after submitting the login form, we perform an assertion to verify that the URL has changed to the expected dashboard page, thereby confirming a successful login. Finally, we ensure proper resource management by closing the browser instance after the test is executed. This structured approach demonstrates how straightforward it is to utilize Playwright for testing authentication flows in web applications, providing clear feedback on the login process's effectiveness. Now, let's implement the following test case for invalid login attempts. This function simulates a user trying to access the application with incorrect credentials, allowing us to verify that our application correctly handles such scenarios. Within the function, we start by launching a Chromium browser instance using Playwright, which allows us to programmatically control the browser. We navigate to the login page of our application and use the fill method to input invalid credentials for the username and password fields. After simulating a click on the login button, the application processes the request. To confirm that our error handling works as intended, we locate the error message element that indicates an unsuccessful login due to invalid credentials. We assert its visibility to ensure the application displays the appropriate feedback to the user, validating our system's robustness against incorrect inputs. Finally, we close the browser to clean up our test environment. This code is crucial because it checks that the application responds gracefully to failed login attempts, which is a common scenario in real-world applications, reinforcing the necessity of thorough testing for authentication flows. Next, we will write the following code to manage user sessions after a successful login. This is crucial for ensuring that users remain authenticated as they navigate through different parts of the web application. First, we launch a Chromium browser instance to simulate user actions. We navigate to the login page, where we fill in the username and password fields using valid credentials and trigger the login process by clicking the Submit button. Once authenticated, we will navigate to a protected profile page. Here, we assert if the URL matches the expected profile page, ensuring the user is correctly redirected after login. Additionally, we verify the presence of a welcome message on the profile page, which signifies that the session has been maintained successfully. This test effectively confirms that once users are logged in, they can access other secured pages without needing to re-enter their credentials. Finally, we close the browser instance to complete the session and confirm that everything functions as intended. This way, we ensure our application's session management is robust and user-friendly. Now let's implement the following code for testing the logout functionality in our web application. This code begins by launching a browser instance using Playwright, allowing us to simulate user interactions. We navigate to the login page and fill in the username and password fields with our test credentials. This step ensures that we are logged in before testing the logout feature. Once logged in, we specifically simulate clicking the logout button. This action is crucial as it represents the process a real user would follow to end their session. After triggering the logout, we include an assertion to verify that the user has been redirected back to the login page. This confirmation not only ensures that the logout was successful, but also validates that the session has ended properly, maintaining the security integrity of our application. Lastly, we close the browser, wrapping up our test. By successfully implementing this logout test, we enhance our testing suite, ensuring that session management is functional and secure, allowing users to log out seamlessly from the application. Now let's see how we can implement our authentication tests using Vitest for better organization and management. We begin by importing the necessary libraries, specifically Vitest and Sync Playwright from the Playwright API. Using Vitest's fixture functionality, we create a browser fixture with a module scope, which allows the browser instance to remain open for the duration of our test suite. This approach reduces the overhead of launching and closing the browser for each individual test. Next, we implement a page fixture. This fixture opens a new page in the browser for each test, ensuring the tests run in a clean environment. Following this, we define several test functions that represent different authentication scenarios. For instance, the test login function navigates to the login page, fills out the login form, and asserts that the user is redirected to the dashboard upon successful login. Similarly, the test invalid login function checks the application's response to incorrect credentials, ensuring an appropriate error message appears. The remaining tests validate session management and the logout functionality, confirming whether the user's session persists across different pages, and that logging out correctly redirects the user back to the login page. By structuring our tests this way, we minimize duplicated code and maintain clarity within our testing framework. As we wrap up, it's crucial to remember to clean up any sessions and cookies when tests run to maintain independence and avoid cross-test contamination. Playwright offers methods to clear cookies and local storage, which could be included in the test setup or teardown processes. In conclusion, we have explored various aspects of testing authentication in web applications using Playwright. So far, we touched on performing logins, verifying sessions, handling failed authentication attempts, and logging out. We've created structured tests using fixtures, leading to better maintainability. In our next lesson, we will delve into how to handle user role permissions in our tests, ensuring that different types of users have access to corresponding. Now let's implement the command to set up our Vitest environment. By executing the command npm init Vitest, you are initializing Vitest for your project. This command sets up a basic configuration and installs Vitest as a dependency, which is crucial for running tests effectively. After this command runs, you will find a configuration file named Vitest config.js in your project directory. This file is where you can customize your testing setup according to your specific needs, allowing for flexibility in your testing strategy. Additionally, if you're testing in a browser-like environment, ensuring that you have tools like JSDOM installed is important, as Vitest simulates a browser environment, enhancing the accuracy of your tests. With Vitest ready, you can confidently move forward to write comprehensive authentication tests, knowing the foundational setup is correctly established. Now let's implement the following testing code for validating our user authentication flow. We begin by importing essential functions from Vitest, such as describe, it, and expect, along with the login user function from our authentication module. Here, we define a test suite labeled authentication tests using the describe function, which helps group related tests together, providing better organization and readability. Next, we create a test case within this suite using the it function to verify that users can log in successfully with valid credentials. Inside this test case, we await the response from the login user function by passing in a valid username and password. With the response in hand, we check if the status code is 200, indicating a successful login. Additionally, we assert that the response data contains a property called token, which is typically returned upon successful authentication. This structure allows us to confirm that the login functionality behaves as expected under ideal conditions, providing a reliable basis for further user authentication tests. Next, we will write the following test to handle invalid login attempts, which is essential for ensuring both security and a positive user experience. The test checks the functionality of the login user method when supplied with incorrect credentials. We begin by setting up an asynchronous test case that simulates a user trying to log in with the username invaliduser and the password invalidpassword. This action triggers a call to the login user function, which interacts with the server to attempt authentication. Upon receiving the response, we assert that the HTTP status returned is 401 unauthorized, which indicates that the login attempt was unsuccessful due to invalid credentials. Additionally, we check that the response data contains an error property, verifying that an appropriate error message is returned. We expect the error message to specifically state invalid credentials, reinforcing the application's ability to provide clear feedback when login details are incorrect. This test is fundamental for validating that your application effectively restricts access for unauthorized users, thereby enhancing overall security. Now let's see how we can implement tests for accessing a protected resource after logging in. This code snippet defines a test case that checks if a user can access the dashboard data when they are logged in. First, we perform a login operation using valid credentials to ensure that the user session is active. By calling the login user function with valid user and valid password, we simulate a successful user authentication. Once the user is logged in, we proceed to access the dashboard data by calling the getDashboardData function. This function is expected to fetch the necessary data for logged-in users. The next critical step involves asserting that the response we receive has a status code of 200, indicating that the request was successful. Additionally, we check that the response data includes the property dashboard data, confirming that the user session is maintained effectively and the user can access protected resources without needing to re-authenticate. This test demonstrates the fundamental principle of session management, which ensures seamless user experiences in web applications as users navigate through different protected routes. Now, let's examine the logout functionality through a specific test case. We begin by simulating a user logging in with valid credentials to ensure we start from a known state where the user is authenticated. Next, we invoke the logoutUser function, which is responsible for terminating the user's session. By asserting that the response status is 200, we confirm that the logout process has executed successfully. After logging out, it's critical to validate that the user can no longer access protected resources, so we attempt to retrieve the dashboard data, which should now be restricted. Here, we check that the response returns a 401 unauthorized status, indicating that access is denied since the user is no longer logged in. This test not only validates the logout mechanism, but also reinforces the application's session management, ensuring that user sessions are managed effectively for security purposes. With this implementation, we can confidently assert the robustness of our authentication system against unauthorized access following a logout. Now let's see how we can implement mocking in Vitest to enhance our testing capabilities. To begin with, we import the Roman 6 function from Vitest and the loginUser function from our authentication module. The primary purpose of this mock is to simulate the behavior of the loginUser function without making actual calls to the authentication service. This is particularly useful when we want to avoid dependencies on the real backend during our tests. Next, we utilize the Roman 6 mock method to define a mock implementation for the loginUser function. By creating this mock, we can specify that whenever loginUser is called, it will return a resolved promise that mimics a successful login response. This response includes a status of 200 and a token, which can be utilized in our tests to confirm that the application logic correctly handles a successful login scenario without relying on the actual backend. This approach allows you to focus solely on testing your application's functionality in isolation. By using mocks, you can also test various scenarios, such as errors or timeouts, ensuring robust error handling in your application. Now let's see how we can implement a mock for simulating a service failure during a login attempt using Vitest. We can utilize the Roman 6 mock function to create a mock implementation of our loginUser function from the authentication module. In this mock setup, we return a function that, when called, is designed to always reject with a specific error response. This error response simulates a server downtime scenario by providing a response object with a status of 500 and a message indicating that the service is unavailable. By doing this, when our tests call the loginUser function, they will receive this simulated error instead of hitting the actual backend service. This is particularly useful for testing how our application handles errors gracefully. It allows us to verify the error handling logic in our components and ensure informative error messages are displayed to users. Such setups are critical for developing robust applications that can manage various failure scenarios effectively, contributing to an overall better user experience. Now let's see how we can maintain test integrity by implementing lifecycle hooks in Vitest. To ensure that our tests run in isolated environments and avoid any potential interference between test cases, we can utilize the before-each and after-each methods provided by Vitest. In our code, we begin by importing these lifecycle hooks from Vitest. The before-each function is used to set up conditions prior to each test case execution. Here, we call Roman 6 clear all mocks to reset all mock states before each test which helps eliminate any carryover effects from previous tests. This is crucial as it ensures that our tests do not yield flaky results due to leftover state from earlier executions. Next, we implement the after each hook, where we can include any additional cleanup routines after each test runs. Although in our current setup we have commented out specific actions, this hook provides flexibility, allowing us to clear out sessions or other setups if needed. By performing these operations, we establish a clean slate for each test, thus reinforcing consistent and reliable test outcomes in our authentication flow scenarios. In conclusion, by leveraging Vitest for testing authentication flows in web applications, we can enhance our testing strategies significantly. We discussed how to write tests for valid and invalid login attempts, managing sessions, performing logout actions, and even mocking functions for a cleaner test experience. To clarify what we've covered, we delved into setting up our Vitest environment, wrote comprehensive tests for authentication scenarios, explored mocking capabilities for effective error handling, and maintained the integrity of our tests using lifecycle hooks. The next step in our learning journey will be to delve into user role permissions and how we can enforce access control in our tests. This upcoming lesson will empower us to create more dynamic applications by ensuring that different roles can access the specific parts of the system they are. Testing Svelte stars is a crucial aspect of ensuring your applications are robust and maintainable. In this lesson, we will delve into the fundamentals of writing unit tests for Svelte stars, focusing on how to properly observe and set star values, enhancing the readability of your tests through strategic renaming of star imports. This ensures not only functionality, but also clarity when others review your code. So far, we covered testing authentication flows in web applications using Vitest, exploring various scenarios like validating access, managing user sessions, and simulating API interactions. Now we will talk about testing Svelte stars and how to ensure your application state is functioning as intended. Now let's see how we can define a simple writable Svelte star to manage user information. In this example, we import the writable function from Svelte star module, which allows us to create a star that can hold and update values. We initialize the user star with an object containing default user properties, specifically a name set to guest and a logged-in state initialized to false. This structure serves as the foundation for our application's user state management, allowing us to easily access and modify user data throughout our application. By using a writable star, we gain the ability to not only retrieve the current state, but also to update it as needed. This sets the stage for our unit tests, where we will observe this star and verify its behavior upon receiving updates. With this star in place, we can later implement tests that will check if the initial values are set correctly and if updating the user state functions as expected. This approach emphasizes the reactivity of Svelte stars, streamlining state management in our user interface. Now let's implement our first unit test for the user star using Vitest. Begin by ensuring that Vitest is installed as a development dependency in your project, enabling us to leverage its testing capabilities. In the test file named userstar.test.js, we import the user star from its module and the get function from Svelte star utilities. This gives us the tools we need to interact with our star. Next, we set up a test suite using describe to group our tests related to user star. Within this suite, we create an individual test case with it to check the initial state of our star. Here, we call the get function and pass in user star to retrieve its current state. This state is then compared to an expected object representing our initial values, specifically that the user's name is guest and they are not logged in. By using expect, we make assertions that help ensure our star starts with the correct values, laying a solid foundation for our tests and ensuring that our star behaves as anticipated from the beginning. Now let's see how we can test the updating of the logged-in state in our Svelte star. In this next test case, we employ the set method on the user star to update the user's information with a new object representing a logged-in state. Passing an object with the name Alice and setting the logged-in property to true effectively simulates a user logging into the application. After making this update, we utilize the get function to retrieve the current state of the user star. This allows us to observe the changes made by the set method. Finally, we assert that the updated value matches our expectations, confirming that the star correctly reflects the user's logged-in status. This step is crucial as it ensures that our star updates not only happen correctly, but also that the application responds appropriately to user actions, enhancing the reliability of our authentication flows. By writing this test, we ensure that our state management functions as intended, fostering a robust application. Now let's take a look at how to enhance the readability of our tests by renaming the import of the star. Instead of directly importing the user star as user star, we can import it as current user. This renaming not only provides clarity, but also gives immediate context about what the variable represents within our tests. Next, we will implement our test suite using this renamed import. We begin by writing a test case to check the initial state of the current user star. By using the get function from Svelte star module, we can retrieve the initial values and assert that they match our expected object. This ensures that the star has been correctly initialized with a guest user. Following that, we will write another test to verify that we can successfully update the logged-in state of the user. We can use the set method on current user to change the state to represent a logged-in user named Alice. By asserting the output after the update, we confirm that the star's state reflects these changes accurately, providing confidence in the star's functionality. Now let's take a look at how to create a derived star in Svelte using the derived function. This function allows you to create a new star that derives its value from one or more existing stars. In our case, we are going to define a welcome message star that computes a greeting based on the logged-in status of the user. We begin by importing the derived function from the Svelte star and also importing our existing user star, which holds information about the user. The welcome message derived star takes user star as its input and utilizes a callback function that receives the current state of user star. Inside this function, we check the logged-in status from the user object. If the user is logged in, it returns a personalized welcome message that includes the user's name. If not, it defaults to a generic greeting, welcome guest. Next, we will need to ensure that this derived star reflects any changes made to the user star. This is crucial as it allows our application to respond dynamically to user states, providing a seamless and personalized experience for users interacting with the application. Now let's take a look at the tests we've written for the welcome message derived star. In this part, we are confirming that it generates the correct message based on whether a user is logged in or not. We begin by importing the necessary components, including the welcome message star and the current user star, which represents the logged-in state. Next, we set up a testing suite using describe, where we outline two key test cases. The first test validates that the welcome message for a guest is displayed correctly. To do this, we retrieve the current value of the welcome message star using the get function, and we assert that it equals welcome guest. This ensures that the default state of the star is functioning as expected. In the second test case, we simulate a logged-in user by updating the current user star with a new user object that includes the name Alice and a logged-in status set to true. Again, we get the value of the welcome message star and confirm that it updates to welcome Alice. This illustrates how the derived star reacts to changes in its underlying star and produces the appropriate output. Through these tests, we ensure that our welcome message logic is robust and responsive to user state. As you can see, unit testing Svelte stars is straightforward, but essential for ensuring your application's state management behaves as expected. By writing these tests, you not only ensure that your star maintains the correct values, but also that other components relying on these star values will function appropriately. It's important to keep your tests organized, legible, and robust. Regularly running these tests as part of your development flow will help catch any potential issues early and maintain a high standard of code quality in your applications. In conclusion, we have explored how to test Svelte stars, emphasizing the importance of observing and setting values and improving readability through smart naming conventions. With this knowledge, you can create reliable, maintainable applications that leverage Svelte's powerful state management capabilities while ensuring your application's functionality through comprehensive testing. In our next lesson, we'll dive deeper into testing user role permissions and access control, which will elevate our understanding of user security within applications. Keep coding, testing. In today's lesson, we're diving into the realm of web applications with a focus on testing service workers for offline access. Service workers act as a powerful middle layer between your application and the network, giving you the ability to craft experiences that function even when the user is offline. Understanding how to effectively test these service workers is crucial for ensuring your web apps can gracefully handle offline scenarios. So far, we covered the significance of testing Svelte stars to ensure application robustness and maintainability. We discussed observing and setting star values, utilizing the Vitest framework for unit testing, and enhancing test readability through strategic naming conventions. Now, we will cover how to test the functionality of service workers specifically for offline scenarios and caching behavior. Now, let's see how we can enable experimental service worker support in Playwright. To do this, we need to modify our configuration in the package JSON file. By adding a script to the scripts section, we can set an environment variable named PW experimental service worker network events to 1, followed by the command to run Playwright tests. This specific configuration allows us to execute tests that involve service worker events, which are crucial for validating offline behavior in our application. By effectively setting this up, we prepare our testing environment to handle scenarios where service workers manage resource caching and request handling, even when the application isn't in active use. This step is essential to ensure that our tests can comprehensively assess the functionality of service workers and how they enhance the reliability of web applications, particularly in offline situations. Next, we'll implement a helper function called Wait for Service Work Activation. This function is essential for ensuring that our tests do not proceed until the service worker is fully activated and ready to cache requests. Essentially, it first retrieves the service worker's registration status. If the service worker is already activated, the function exits early. However, if it is not yet active, the function sets a listener to wait for the controller change event, which signifies that the new service worker has taken control. This makes sure that any caching operations in our tests only occur after the service worker is fully set up. Now let's implement the disable network function, which serves to simulate an offline scenario during testing. This function utilizes Playwright's routing capabilities to intercept all network requests. By calling routeabot, it effectively prevents any outgoing requests from being processed, thus mimicking a complete network failure. This is invaluable for testing how our application behaves under offline conditions, allowing us to confirm that it can gracefully handle scenarios where data fetching fails due to the absence of network connectivity. Now let's write a test case that uses the functions we defined earlier. The purpose of this test is to ensure that our application maintains its functionality even when offline. We begin by simulating navigation to the birthdays page, which triggers the service worker to cache the necessary resources. After this initial call, it's crucial to ensure that the service worker is fully activated using our previously defined Wait for Service Work Activation function. Next, we simulate an offline scenario by disabling network access with the Disable Network function. This is where the magic happens. Once we attempt to go to the birthdays page again, the app should rely on the cached resources. We then check if the relevant element, birthday list, is visible on the page. This assertion confirms that our service worker effectively caches resources during the first call and makes them accessible when offline. Thus, this test solidifies our confidence in the offline capabilities of our web application, highlighting the vital role service workers play in enhancing user experience under varying network conditions. Next, we will implement a service worker to enable offline access for our web application. The first step is to listen for the installation event, which we accomplish by adding an event listener. Within this listener, we call the Add Files to Cache function, passing in the cache ID and the assets that need to be cached. This ensures that all essential files are stored locally when the service worker is installed, allowing them to be available even when the user is offline. Now let's look at the Add Files to Cache function. This function is crucial for our caching strategy. It begins by opening a specified cache using the cacheSOpen method, which allows us to either create a new cache or access an existing one. Once we have the cache, we utilize cacheAddAll to add the list of assets to it. This process ensures that important files, such as CSS, JavaScript, and images, are saved and retrievable during offline scenarios. This caching mechanism is essential for providing users with a seamless experience, ensuring that they can access the application even with intermittent internet connectivity. With these foundational pieces in place, our service worker starts to take shape, ready to manage caching and offline functionality effectively. Next, we will implement the Delete Old Caches function, which plays a vital role in maintaining an efficient caching strategy. This function is designed to clean up any outdated caches once a new service worker is activated. By doing so, it ensures that only the most current assets are stored, preventing unnecessary storage usage and potential issues with stale data. Now let's take a look at the implementation. The function begins by taking in a single parameter, cached, which identifies the cache that should be preserved. It then retrieves a list of all existing cache keys using caches keys. The function iterates over these keys, and for each cache key, it checks if it does not match the provided cached. If there is a mismatch, the function proceeds to delete that cache using caches, delete key. This systematic approach ensures that old caches are removed, thus optimizing the app's performance by only retaining essential and up-to-date cached assets. Cleaning up these old caches is crucial for maintaining a streamlined, responsive application as users interact with it offline. Now, let's implement the Fetch Event Listener in our service worker, which plays a crucial role in managing network requests. This listener is designed to intercept all fetch requests made by the application, specifically focusing on GET requests. When a fetch event occurs, the listener calls the FetchWithCacheOnError function, passing the cache ID and the requested resource as arguments. This approach ensures that we efficiently handle network requests by trying to fetch resources from the network first. Next, we need to look at the FetchWithCacheOnError function, where we will attempt to retrieve resources through a network request. The function first opens the specified cache and initiates a fetch request for the desired resource. If the fetch is successful and returns a response with a status of 200, we store a clone of this response in the cache. This caching mechanism provides a backup for offline scenarios. However, if the fetch request fails, perhaps due to a lost network connection, the function gracefully falls back to retrieving the resource from the cache, ensuring that users still have access to the content they need even when offline. This functionality is central to delivering a seamless offline experience in our web application. Now let's take a look at how to effectively test the Add Files to Cache function using Vitest. First, we establish a testing suite with a description that reflects the function being tested. Inside this suite, we define a variable for the cache, simulating its functionality with a mock object that includes a spy for the addAll method, allowing us to track calls to it. Before each test runs, we use the beforeEach method to reset the state by creating a new mock cache and spying on the global cacheSOpen method. This ensures that each test operates with a fresh environment. Next, we write our first test case to verify that the function opens the cache correctly with the specified ID. By calling Add Files to Cache, and then checking if cacheSOpen was called with the expected cache ID, we validate this functionality. In the following test, we check the car behavior of the function, ensuring it adds all provided assets to the cache. We prepare an array of asset URLs, execute the function, and then confirm that the addAll method was called with this array, ensuring that the caching mechanism works as intended. This comprehensive testing approach provides confidence in the reliability of our service workers' caching functionality. Similar tests can be constructed for the delete-old caches and fetch-with-cache-on-error functions, allowing us to isolate and verify that each piece of our service worker works as intended. By leveraging Playwright for end-to-end testing and Vitest for unit tests, you can create a comprehensive test suite that covers both the functionality and performance of your service worker. This ensures your application provides a reliable offline experience, a vital aspect of modern web development. As we conclude our exploration into testing service workers for offline access, remember that thorough testing is key to building resilient applications that provide seamless user experiences, regardless of network conditions. So go ahead and implement these practices into your projects and enjoy the enhanced reliability of your web app. In this final section, we will do a project challenge to apply what we have learned so far. Your task is to create a fully functional web application called **birthdays**, where you will implement a user-friendly interface to manage a list of birthdays. You will be using SvelteKit for the front end and applying the principles of test-driven development, TDD, throughout your development process by utilizing Vitest for unit testing and Playwright for end-to-end testing. The application should include features such as a home page displaying upcoming birthdays, forms to add and edit birthday entries, and comprehensive input validation. You are encouraged to follow the red-green refactor workflow, ensuring that tests are written and passed before implementing functionality. The project structure is clearly outlined for you, and the complete source code, along with documentation, will need to be shared via a GitHub repository. This is your opportunity to challenge yourself and build something meaningful, so take the skills you've acquired and bring your birthdays application to life. You can find the final project details in the GitHub repository linked